With new hopes and aspirations, Robocon is returning to India in 2022. It will be hosted by IIT Delhi for the first time in Robocon's 20-year history. Delhi is ready to be a grand host. Based on India's traditional sport Pittu, the theme this time is Lagori. Amidst modern challenges and future problems, it is expected that robotics will open new avenues and possibilities at this Robocon.
Over to you, Venkat. You can start.
Yes, sir. Good morning, everyone. The number of participants, let me cross-check. We have some more.
That is okay, Venkat. We can go ahead and you just in between just keep checking those who are joining.
Yes, sir. So today's session will cover all electrical and computing design lectures, as well as some demonstration on electro-pneumatic systems. And in the second half, we'll show how the electrical and electronic components are being integrated on the robot and how we test them to make sure they're in working condition. And so let's start the first session by Professor Sunil Jha. He'll be giving an overview of the electronics on the robot. Sir, it is over to you.
Thank you. Thank you, Venkat. And good morning, all. Thanks for joining again for this session. And I hope that yesterday's session will be interesting to you. So what we will do, we'll just quickly start discussion for today's session. Let me share my slides. Just give me a minute.
Meanwhile, Sunil sir starts the sessions. I would like to ask whether the participants started interacting with each other as per the groups we have given.
Yes, so we started interacting with them and make a WhatsApp group and started working.
That's great. Great to hear. And what about others? Okay, sir. Let's start.
Yeah, let me start, I think.
Yes.
So this is what we had planned for day 2. Certainly we will be focusing more on the brain and the programming of the robot. Yesterday we created the body of the robot. So there's a physical system that we have created, and then we have just made you familiar with the process of manufacturing. And today we will be focusing on the brain of the robot. And then we'll also be talking about the senses and the programming part or the training of that brain for performing certain functions. So that is how the whole session is being aligned. And certainly there is a part on the electro-pneumatics that I will be discussing, which would be a kind of muscles for the robot. So that's interesting that you will be creating in a full robot starting from the basic physical system, and then we'll be talking about the electronics today. So before I just start, I just want to have a quick discussion with you, and then I will discuss on that. So when we talk about the electronics, basically electronics for the robot, I just want to have a quick input from all of you that what you understand when I talk about the electronics for robot, what you will be looking forward. So please respond, then we'll discuss on this, because let's make it more interactive and understandable. Then it makes sense, because I understand the group here is from the various streams. Some of you are from the electronics and electrical systems, electrical engineering. Some of you are from mechanical, some of you may from computer science. So let's try to come out with a very basic understanding about the electronics of the robot. So you have seen the robot physically that we have created yesterday. Now, when it comes to operate that robot, certainly we look forward that it has to be operated by the electronics. Suppose if there was no electronics, let's talk about that. And if I would like to control this robot manually, when I say electronics means I'm not talking about the motors are still be there, and I would like to directly operate these motors from the power source. So what could be that method? Can anybody tell? Forget about the controller right now, forget about the brain. If I would like to manually operate this robot, what should be the methodology?
Maybe we could use an engine or something like that.
No, I'm still be keeping, not going into the IC engine. I'm still be keeping there the 4 motors that we have connected yesterday. Let's start from there. So if you just see that whatever we have created yesterday, it's a frame. We fixed up the drives, the motors are there. And then after that, now we are talking about adding the electronics onto that. So let's forget about that, what electronics should come. We'll be just starting from the understanding there are 4 motors, and I would like to make the robot move, and I would like to operate it manually. So certainly all of you may be understanding the motors, how they are being operated. Yeah, you can put on the chat also, I can read. Yeah, Aditya mentioned that it's a DP-DT switches. Good input. Anybody else? So idea is that our intent is that we would like to control the rotation of the wheels when the robot is supposed to move. And in a certain fashion, if you control the wheel motion, then you will be able to move the robot in multiple directions. And that is the intent. So we are using a DC motors, the brush DC motors with certain gearbox connected to them. And whenever we connect it to the power supply, so for example, let me talk about this. So if I have a motor over here, which is a DC motor, and you have seen that through the various mechanical linkages, you are coupling it with the wheel. So I'm not drawing all those elements, but I am just drawing, this is your wheel. And if you would like to rotate this, and we know that we have 2 terminals to this motor. So what I'm supposed to do, I have to just connect a battery or the power supply to this motor. So if I just want to control through push button, I can just draw like this. So what you can do, you have a push button, you have a plus 12 volt battery. So this is plus minus, and then there's a plus minus terminal of the motor. So very simple understanding that whenever you press this push button, your motor will rotate, fine. And then once you are able to control multiple motors in certain fashion, you will be able to make the motor platform moving. So what Aditya has responded, certainly in earlier days, I'm not sure if you have just keep watch of the way Robocon people have developed. So yesterday we were showing it a very fancy this PS4 through which you will be able to wirelessly give the command to the robot and able to control its motion. Earlier days, people were using the wired connections to the robot, and certainly kind of in a configuration where you will be designing in a handheld pendant kind of thing, where you will be keeping multiple push buttons like this. So forward, reverse, something else. So these are the push buttons that you can have on the pendant, and then through the wired connections, certainly with the help of some switches, you will be able to navigate and you will be able to control the motion of the robot. Is this understood by everyone? Because people are not speaking, it's very difficult to understand. If you are from a mechanical or you are from a different stream, are you getting what I'm just trying to convey?
Yes, sir.
Good. So in that case, now what is our intent of putting the electronics onto the robot? Can anyone explain that? See, unless we understand why we need electronics, there is no point in discussing what we are going to do with that. Certainly, we'll give you some schematic circuit diagram, block diagram, and you will be able to put into that. But without understanding, it doesn't help much actually. So I just want to build up that understanding. What all electronic systems are required, for what purpose we are going to put them. Then certainly we'll talk about how to integrate them, right? So first, let's understand why we need electronics onto the robot. For autonomous control, good. So you would like to have robots either fully autonomous, semi-autonomous, or as I was mentioning that these days, even the manual robot, we would like to control through the wireless communication. We don't want to put the wires because wire will be creating a lot of issues because somebody has to move very close along with the robot while the robot is moving onto the field. So these wires may entangle with other stuffs, creating an issue. So wireless is always better to give a command to the robot and control. So even we are controlling it manually, we still look forward for some kind of a communication should happen. So that is the idea that we want the electronics. When we say autonomous control, what we want to control? We are talking about the same thing what I just explained with this example. We want to control the motion. So motion is a very important part of the robot. Please understand, because we are talking about the autonomous mobile robots. So it's a mobile platform that we are building and that we have already built, and we would like to control its motion. Apart from the motion, so one is the mobility of the robot, because we want to take it to the different locations, certainly speed and directions. That's very important, because if you want to move the robot from one point to another point, one position to another position, we would like to have all these kind of controls, speed, direction. Now, when we talk about the mechanism, certainly then these mechanisms are not moving the robot, but they are moving certain linkages onto the robot. As you have seen that yesterday, while throwing a ball, you will be controlling some kind of an actuators, either it's a rotary actuators or maybe linear actuators. You will be controlling them so that whenever it is required, you will be able to actuate those mechanisms. So that is the idea, that we would like to exercise some control on the robot. And then we would like to also implement the motion control of the whole robot platform around it, right? So that is the basic purpose we have understood now. The second thing, when we talk about the autonomous, it's more important that your robot should also be having a sense or the perception about the environment, so that it will be able to understand where it's supposed to move. You can give the fixed program with the commands, so it will be moving around in a certain path, but at the same time, we would also like to capture the feedback from the environment. So that is the way most of the autonomous systems are supposed to work. So idea is that to give some input to the robot. Now, these inputs are coming from the sensors on board onto the robot, or these inputs can be given manually also through the wireless communication. So that is another requirement that we have to look forward. So we have motion, the mechanism actuations. So we can say that mechanisms actuation on robot for various activities. We would like to have perception built through sensors. Fine. So these are the basic need that we would like to put some electronics onto the robot. Right. Now we will go step by step. So first we talk about the brain actually that is available, because that from there we will come to that how we will be controlling the motion and the various things. So the board that we have used on the sorry, on the robot is we have multiple options. As I was keep telling you, there are multiple options for these hardware these days, because we are lucky enough that semiconductor has developed to some to that extent. You have everything on a size of a palm or even smaller than that now. So that's a era we are talking about building the robots. I think the time when we started thinking about the robot and the electronics, this kind of flexibility is not there. And we are certainly worked on the microcontrollers directly, writing the assembly code actually. So I remember my days when I was working on microchip PIC controllers. So these are the microcontrollers. We need to understand a lot of electronics architecture inside the controller board or this microcontroller itself. Then only we will be able to make use of it. These days it has been simplified a lot actually, because certainly a lot of revolution happened with this Arduino platform that has been built up, so that it doesn't emphasize a lot on understanding what is happening inside the controller. They will be directly giving you an access with the help of a library. You can easily write the code. Now, when we talk about the controller, that is the brain. So certainly we are talking about these digital microcontrollers or digital microprocessors, which will process the information in digital format actually. And then this is the brain. Now we need to connect the external peripherals to this brain. So I'm not going to discuss the architecture, but I'm just going to discuss what all options are available to interface with this board. So can anyone tell what all options are available on this board? What kind of interfaces you have on this board? So I hope, hopefully you understand this electronic board. There's a microcontroller onto this. So if you look at this, this is the microcontroller chip on the board. Then you have various interfaces provided to you. So these are the connectors through which you will be able to interface external devices to this board. What are these interfaces? Can anyone explain? Shall I call the name and then ask, or you will be telling on your own? Dhananjay?
Sir, the upper one is for the analog and the right side one can for the digital.
Yeah, so fine. You are saying that we have some interface for the analog, some are
Yes,
for
sir.
the digital. Can I see the hands who understand what is analog, what is digital? Can I see the hands? Those who are familiar with what is analog, what is digital, can they raise their hand? Yeah, 1, 2, 3, 4. What about others? They didn't understand this, or they don't want to speak about this. Yeah, so I can see at least 5. 50%, I should be expecting at least 50% of this community who are joining this bootcamp. They have a good passion for the robots. And see, those who have passion for the robotics, they already started activities during the school days. That is what I always observe. And you all are into engineering. Certainly you have some understanding or good understanding about the basic of the robots. So I still see 7 only out of this number. I'm still waiting this to reach at least 50%. No? Yes, Bihani. All of you did this basic electronics course
Yes,
in
sir.
the first year itself, right? What I understand.
Yes, sir.
Yes, sir. So when we talk about the digital signal, when we talk about the analog signal, do you understand what is the difference? Or you can just give an example, what could be a digital and what could be the analog?
Digital signal can be the signal from the processor to the computer, and analog signal from the any physical signal like sound wave.
Okay, so you give some, yeah, you come out with some understanding. So when we say sound wave, it's the varying signal actually. That is what we are trying to capture. So the magnitude of that signal is varying. Thanks. I think those who have raised their hand, they can lower it up. So idea is that some of the signals are just changing the state. So if it is either high or low, either 0 or 1, we put all those kind of signals into the digital, because there's a binary state or the 2-state signals. When we see there is something which is varying continuously. For example, if I have a temperature sensor, so temperature sensor will be giving me a continuously variable voltage because it has to be proportional to the temperature that it is sensing. So that kind of signal which is continuously varying between certain voltage limits, that is the analog signal. The signal which is just changing the state, high or low, and 0 or 1, 0 volt or 24 volt, 0 volt or 5 volt, all these signals are the digitals. It's a 2-state binary signals, which are calling as a digital signals. For example, if you are pressing a push button, so this button pressing is either giving you 5 volt or it is giving you just 0 volt, right? If you're not pressing, it is 0. If you're pressing, it is 5 volt. So that is how the digital signals are there. and there are analog signals. So now let's quickly have a brainstorming on the robot. Which are the digital signals and which are the analog signals? Is there any analog signal that you are dealing with, or it's all digital signals you are supposed to handle? Yes, Gauri Patil. First, tell me what are the digital signals you are supposed to handle, and from where these signals supposed to come?
Signals from Hall sensors or
Correct.
discrete values.
Correct. Correct.
Even in signals from encoders are mostly digital signals.
Correct. So, so in that case, we understand most of these inputs are coming to the controller from various sensors. And certainly, when we talk about the encoders, which type of signal it will be, analog or digital?
Digital, because the values are discrete.
Yeah, correct, correct. Because the pulses are coming actually. So the signal state is changing between the 0 volt and 5 volt or 0 volt or 3.3 volt. And we are just counting those number of pulses as an encoder input. Good. So we understand that there are sensors which will be giving these signals, which are either in the form of a digital or analog. For example, I'm measuring the distance with the ultrasonic, then distance will be just proportional to the voltage that I'm getting. So that kind of input is basically an analog to my board. So we understood that there are some inputs coming to this board. So we will be saying there are, let me just put, there are certain inputs to this board. And there are certain outputs we would like to generate out of this board. These markers, I'm just putting it not on the respective pins, I'm just giving for the whole board. So there are certain outputs we would like to generate. What are these outputs? Who will tell? Asmin?
PWM signals.
Yeah, so outputs basically, we would like to create again the digital outputs or analog outputs. Mostly we are producing the digital outputs. And what you have mentioned is the signal used to control the speed of the motor. So we say pulse width modulated signals. So certainly it's a kind of a digital pulses that we would like to generate to do this kind of a control. Good. So then we understand there are certain inputs coming to this controllers. There are certain outputs that I'm supposed to generate. Now, second thing, which is very important to understand those who are not from a deep electronics background, how you will be physically connecting these devices to this controller board, because there's a limitation on the kind of a voltage and the current this board can provide. So that's important. When I say I would like to control a motor, I should understand how I should be connecting and interfacing to this board. So that is the basic understanding that is required whenever we talk about the Arduino or whenever we talk about Raspberry Pi or any kind of a digital controller board, we need to understand that. So before we select the board, we should understand what is my requirement, and based on the requirement, I'll just pick up the right board for my application. So this board, if you just look at this, there's a lot of IO terminals. IO is basically input and output that we are discussing about. So it has 54 digital IO terminals. So lot is available for you. And out of that, it's 14 are PWM that you can program them to produce the PWM outputs. So that is the advantage of having this Atmega 2560 board or the Arduino Mega 2560 board. It has 16 analog inputs. That's again a very good that you can interface 16 analog sensors or the interfaces to this board. So again, very nice. There are UARTs basically. Anybody knows what is UART? Though it is written on the slide itself, it's a hardware serial ports. So some signals we are communicating with the controller in the form of an analog voltage. Some signal we are communicating in the form of two-state inputs that are coming to the board. Sometimes you would like to pass the value. For example, if you are just using in the PS4 device to give some input to the controller regarding the speed. So you may specify the percentage speed. For example, I said 40%, 50% of the rated speed. So some value you would like to communicate to the board, and some inputs you would like to read out also. So these kind of a data exchange can be happening on some kind of a bus interface. Normally, I'm sure that all of you understand what is USB. So it's a universal serial bus. It means through buses, we are exchanging much more data rather than just a state or a single voltage in value actually. So these serial interfaces are there through which you will be able to communicate in a digital format. So you will be exchanging the bytes of the data through the controller, and then either your sensor will be passing that information. So controller will interpret that. This is the speed of the controller board. So you can see that so it's not very high. It's not appealing too much when we are dealing with a gigahertz kind of a speed in the microprocessors. But believe me, this is still very high and good enough for controlling a robot. So you need not to worry about the speed too much, because the instructions that you are executing for the basic controls are not running at a very high speed, right? Then we will be having the operating voltage for this board, and certainly the controller operating voltage is different. So can anybody tell what is the operating voltage of the microcontrollers?
5 volts or 3 volts?
Yes, correct. So it's a 5 volt or 3.3 volt. Right. So these controllers are normally, say these are the TTL levels and these are CMOS levels. So it's a 5 volt or 3.3 volt. But batteries are not normally available in this voltage level. So you didn't find any battery of 5 volt or any battery of 3.3 volts. Cells are available in the different voltage levels. So normally we put multiple cells together to create the battery. And the batteries are available in the multiple of 3.7 volt if you are using a lithium ion batteries. So we normally have, or either you are giving through the adapter or the SMPS over here, then you will be end up in getting much more voltage as an input to this. How this is being converted to 5 volt to 3.3 volt? Anybody else? So my controller needs 5 volt or 3.3 volt, but my input battery is giving me something around 6 to 12 volt, any voltage in between. How you will be making it 3.3 volt? No, step down is fine. I'm asking about what technology you will use to step down. What step down normally, when we understand the initial days, it's in a transformer. So we normally learn the step up and step down transformers. So these days you see that we are not using transformers at all. So how, because this board, if you can see, it doesn't have any transformer as such to step down. So how these step down function? So if I ask you to find out an electronic hardware that will help me in getting 3.3 volt out of this 6 to 12 volt input, what you will select actually? Yeah, good. So voltage adapter, or we normally call it a voltage regulator actually, because it's, yeah, that's good. That's right. So voltage regulators are the devices, that's a semiconductor devices available and readily available to put on the board. So what I can see, if you just try to understand, this is the voltage regulator that you can identify on the board. So these regulators are available for the fixed voltage conversion, so that you will give certain range of the input and it will be precisely giving you 3.3 volt. Regulator is very important because irrespective of the voltage input variations, the regulator is regulating the output within certain value. So plus minus 10%, plus minus 5% variation, because all your digital electronics working within this plus minus, I think 10% variation. So if you are giving 5 volt, it means 4.5 to 5.5 is acceptable. So that you can find out from the data sheet. So we would like to precisely control, irrespective of the load, irrespective of the input, the voltage level should not fluctuate beyond this. Otherwise, your whole circuit functionality will get destroyed. Right? That's a very important part. So we need to go with a precise voltage regulators. So that's a very important part in the electronics to understand, because the power distribution in the robot is again a very important area to understand. Good. So you have some idea on this part. So this board have its, most of the boards comes out with their own regulator circuit on board. That's how they are giving you, either you provide through the USB or you can put an adapter over here. So this will regulate and then it will provide the necessary voltage to the controller. Now, I was just mentioning about the voltage level and I was talking about the current actually. Anybody has an idea how much current each pin will be able to supply? So these digital pins are here on board. What kind of current you can draw from these pins? Very important parameter. Most of the students make mistakes and they burn out these boards. That is a very critical parameter to understand. So whenever we use any of the digital controllers, there is always a, so microampere, even better, actually, we still have a flexibility, because normally we used to run the LEDs easily with the individual pins. So this is possible. Anybody else want to respond? So these are some of the parameters you always have to look into the data sheet whenever you go for selection of the electronics. So normally it is 10 to 20 milliamperes that you can source from a pin. So that's an important part over here. But believe me, with the 3.3 voltage as an output and 10 milliampere or 20 milliampere current, I can't run any of the motors. Is that right? Yes? Yes or no? Yes. So because now let's come to the output that we want to generate. What exactly we want now? What is the voltage or current levels of the motors that we normally operate? So you have to answer. Yeah, we are discussing. Na? So whenever you will be coming here and we will be doing this exercise, certainly we would like to interact and discuss on this. So that's what I just want to have a quick dialogue with you to just explore the understanding on this. So what would be that voltage and current of these motors that we are using? How much voltage that they are? Yeah, 12 volt, good.
12 to 24 volt.
Yeah, 12 to 24 volt, good. And what is the current actually? That's an important parameter. So voltage, we understood that they require little higher voltage. And what is the current?
Depending on the motor from.
So you can just specify any range actually. I just want to get a sense of that. What's the range in your mind?
Up to 13 ampere.
30 ampere, yeah. So it can be ranging from 1 ampere to 30 ampere, depending on the kind of torque you would like to produce, the kind of power you would like to produce from these motors. So good. So now we have a limitation that we are having 10 to 20 milliampere current coming out of this at a 3.3 volt. And I would like to operate a motor which will be requiring a 12 volt. And so my motor requirement is 12 volt, maybe let's say the 15 ampere. Each motor will be requiring this. Now, how I will be connecting this to this controller board? Anybody?
Relays.
So using motor drivers.
Good. So relays, you have given a good input. You have given the inputs motor driver. Wonderful. So I that's what I was expecting. Yeah, this audience which I'm interacting with is a robot enthusiast. They would like to build a robot. See, unless you understand these basic minimal things, it's difficult to put electronics on the board. Otherwise, whatever platform we are created yesterday, somebody has to push it and then make it moving. Unless we give the brain to that robot, unless we give a proper controls to the robot, it's not possible to make the robot moving and performing certain tasks. So good. I think some of you are speaking up, but at least I would like to understand the others also. They should also be responding. To get a sense that you have some idea about these basic understanding. So this is all about the Arduino. So if you see that these are the interfaces available onto this board. So you have a USB connector, you have a controller over here. This is your controller. Then you have rightly mentioned there's a digital IO pins available. These are the communication pins for the various communication buses. You have a digital IOs over here. This is basically for directly programming the controller, that in-circuit serial programmer, ICSP is there. Then you have analog input pins over there. You can reset the controller with this button. These are the power pins. You have distribution of the 5 volt, 3.3 volt ground, because you will be connecting something to this board which requires a power also. So some power can be drawn from this board itself, right? So that is about the Arduino. The board that we are, second board that we will be using in the platform is this one. This looks very nice, small, compact. The additional advantage with this board is that it is having a wireless communication. It's a wonderful feature on this board, because in the previous board, you don't have that flexibility. So any communication you would like to do with a wireless, in the previous board, you're supposed to add additional hardware to that. So maybe you have to plug in something on a USB interface so that you will be communicating on Bluetooth. If you would like to use a Wi-Fi module, then you have to place in a Wi-Fi module and connect appropriately with the controller. So this is the board that has that capability, that if you can see here, it is in a Wi-Fi, Bluetooth low energy, all are available. So this wireless module is taking care of that communications. apart from the basic logic control, basic signal interfacing, it comes out with a communication which is in a wireless, and that's giving you an advantage on this. So this board has a lot of serial buses available, and then IOs available. So a lot of capability as compared to that. So it has an on-chip Hall sensor. Yeah, the speed is also very high. 40 megahertz is the crystal that has been used over here. It operates at 3 to 3.6 volt. That's the important part to understand. So whenever you go with a data sheet of any of the controller, please look at these critical specifications. Then only, because if you are going to interface any kind of a 5 volt device to this, you should be understanding whether this pin will be able to source 5 volt or it will be 5 volt tolerant or not. That's simple. Otherwise, for 3.3 volt controller, if you give 5 volt, it will damage that pin. So just be careful on that part. Operating current is 80 milliampere. Minimum current delivered by the power supply 500, because again this will be using a regulator. If you can see here, every boards are coming with this kind of a regulator, because even the 5 volt USB you are connecting over here, then you will be regulating to give a 3.3 volt to this, right? So this is there. The operating temperature range is also specified. I think that is good enough. Rest of the things you will get in the datasheet. So we all understand there are the pins over here. These are the digital or analog input pins, but we need to see whether analog is available on this. I can't see immediately on this board. So mostly of the pins are the digital pins over here. So in that case, we need to see how you will be giving the analog signals. So you may use an additional boards for that. So this is the basic understanding for this controller. Pin details you will find out from the web itself. So you can just either look at the data sheet of this. So you will get to know GPIOs are the general purpose input output pins, and most of the pins are multiplexed. When I say multiplex, means they have more than one function. Normally they are working as a GPIOs, as you can see here. So these are all IO pins available, but additionally, whatever additional colors, yeah, analog is also there. You can see this ADCs are there. So you see these are the ADCs. So you can have good, I think more than 10 analog channels. Yeah, it's there. So it has, because though the physical interface to the controller is limited with the number of pins, but they are multiplexed in the function. So you'll have all these pins available onto this controller. A good understanding of these pins are important before you go for the interface part. Right? Then these days we have a computer also available in the size of a palm. So that's how the Raspberry Pi revolutionized everything what we are building today. Because the capability that comes with the Raspberry Pi is much more than what the controller board we are talking about. But there are pros and cons of both the kind of a selection. It doesn't mean that a very high speed computer is always good for all kind of functionality. As you can understand, if I ask you to do some basic calculations, you will not be recommending computer. You will say you can do with the calculator. So we need to understand where we need to fit the calculator and where we need to fit the computer. So that's how this Raspberry Pi 4 comes with a very high RAM also. In fact, after this also the 8 GB RAM variants are available. So that's another choice. So anybody just want to mention what is the difference if I put on a Raspberry Pi and with the previous two boards that we were discussing in terms of writing the code and the operations part? Anybody would like to give some inputs? I'm sure you might have handled these kind of boards, no? So then I have to call only, then ask, because you are not responding on your own. GDR Shashidhar.
So we can directly connect it as a computer, and we can directly.
Have you seen these boards? No? You have already seen these boards, no?
Yeah, sir.
Yeah. So in terms of programming or in terms of environment for operating on these boards, what is the actual difference?
Like for Arduino, we have to just program it in like online or the additional application we can program it.
Correct.
But in this, we can run the whole OS.
Yeah, that's what I want. So you rightly mentioned. So we are able to run a complete operating system onto this board. So it means that once you have an operating system, it's almost like in a computer. Either you run the Raspbian as an OS, or you can run a Ubuntu as any Linux operating system onto this board. And you have a display interface also. You can connect the monitor. You have all sort of required interfaces for the Ethernet connectivity. Wi-Fi is also available. You have the IOs also available onto this. So it's a kind of a mix of both the microprocessor and the microcontroller. You will get the both kind of an advantage on it. So you can directly interface with the IOs here. And at the same time, you will be able to run the OS onto this board. So you can directly writing the program inside the board, because as the way you are creating files in any of the operating system, you can create those files and then execute that code directly onto the board. And it has a good capability because there's a 64-bit quad core processor. So that's a very good processor on board that is able to do some kind of a good processing for you also. That's advantage over here. Thanks. I think you have given right input. You have all the physical LAN interface as well as the USB 3 interface over here. And this is operating with the 5 volt 3 ampere by the USB port. So that's a and it has an SD card option. So you can have a file system also. You can store your data, store your files on board itself. The previous controllers are very limited onto the memory, but they are still good for some functionalities. That's a quick understanding on this hardware only. And these are the pin details. Certainly you can find out and understand. So every board you have seen that they have the GPIOs over here. They have other interfaces in terms of the serial buses and then power supply. So you need to find out where exactly you are interfacing, which hardware to this controller board. Good. So we understand, but most of the controllers are not going to give you more than milliamperes of the current. That is understood. And they are not going to give you more than 3.3 or 5 volt. So now our challenge is basically how to deal with the motors and the hardware that we are supposed to control, right? So, and this is another advanced board. So if those who are willing to do even more AI related programming on the robot, they can go for this NVIDIA Jetson Nano. This is a starting board for this with a GPU. It has a 128 core NVIDIA Maxwell GPU. And then it also have whenever we have a board with a GPU, it always comes with a CPU. So it's a mix of both CPU and the GPU capabilities. So you can do the processing as required actually. So it's again a quad core A57 CPU on this. It's a 4 GB RAM is available under this. So this is again good for all kind of an AI and the data processing that you would like to do on board. Again, the capabilities varies, the cost varies. So starting from a basic ESP32, starting from 500, 600 rupees, Arduino will be again the similar range from around 1000 rupees. When we come to the Raspberry Pi, it will be coming in 3000 to 4000 rupees. And when it comes to the NVIDIA Jetson, it is coming around 9000 to 10,000 rupees. So as the capability increases, the cost increases. So again, you will find it out how it can be used and where exactly you want to put for various functionalities. Right? Good. So the challenge comes over here. Now our challenge is basically to control this brushed DC motor that we have added in the robot yesterday. How to control this? That is what the basic technology is very clear that there are two terminals onto this motor. And if you have to connect the power supply to this in a particular fashion. So if you connect the plus to plus, you will get one direction of the rotation. If you connect minus to plus and plus to minus, you will be able to rotate in the opposite direction. So clockwise and anti-clockwise rotations can be done if you just connect the polarity of the battery differently to this DC motor. That's a basic understanding for all the DC motor that we are supposed to use. So this is the thing. Now we understood this. Now our intent is that I would like the robot should be operated with this kind of a motion control. And to some extent, we would like to control through the controller, and to some extent, we would like to control it manually as well. So let me just give you a quick understanding on this. As some of you are giving input, it can be done with the switch also. So there is a possibility you will be just doing the switch on and off. So you will be making motors on and off, and you can put multiple switches to design a pendant through which you will be able to make the robot move forward, robot take a turn, and robot move left or right, or it can stop also. Suppose if I'm using these push buttons, and how I can make the robot turn. So if I'm just using a simple on-off switches, I'm not talking about reversing the polarity right now. So just discussing about the left circuit only, this circuit only. So if I'm using a simple SPST switches and put this switches, 4 switches for 4 motors actually. Now, if I would like to move forward, certainly I will be making all the motors moving and powered on, and they will be moving forward. Certainly, unless you are not reversing the polarity, you can't make the robot moving backward. But I can take a turn. Can anybody explain how can I take a turn without changing the polarity over here? So out of the 4 motors, if I'm just making them power on or off, how can I make them robot to take a left turn or right turn?
So we can use side 2 motors to make forward.
Yeah, so what you can do, you can just create a kind of a center for rotation, and then you will not be powering those motors, and only one side motors can be powered, so it will be able to rotate. So that if you have these 4 wheels like this, what you can do, you can just stop these motors and just make these motors moving. So then it will be taking a turn around this. That's just a crude understanding. So even with the just on and off, you will be able to do that. I'm not saying you should do this. There are better methods available how to control it. Then this is something has been answered. I think Aditya has answered this, that DP/DT switches can be used. So dual pole, dual throw switches are like this. So if you can look at this, these kind of switches have been used a lot earlier days when people are creating manual pendants. So if you just toggle it this direction, it will move the robot forward. If you toggle it this direction, it will make the robot reverse. And once you release it, the center position is the off. So that way I will be able to control each motor in any of the directions, forward, backward, and I will be able to stop it also, right? That's a way it's supposed to work. Now, what is inside these DP/DT switches? So that's a wiring that if you can look at this carefully, you will understand that nothing tricky over here. From the battery source, what we are doing, we are just terminating the battery here, so that the positive and negative of the battery will be connected over here. This is your positive terminal, this is your negative terminal, fine. And what I'm doing, I'm just connecting the motor terminals to this center point. So if you look at this, this motor is connected over here. So if you can, this motor terminal is connected at this point, and there's another motor terminal connected at this point, fine. Now our intent for reversing the direction of the motor is very simple, that I would like to just reverse the polarity to the motor. So, but we have fixed this motor connection to the switch. Only thing what I can change the polarity on the switch itself. So one set of switch pair here, if you can see that one set of the contacts over here, I will be just placing plus and minus, and then on other side, I will be just reversing minus and plus. So if you slide the switch on this side, it will be connecting this to plus and this to minus. If you slide the switch on the other side, it will be connecting this to minus and this to plus. So that is the way I will be easily switching the polarity. So that's how it will be. Once you push it forward, it will be making these connections. If you just make this moving on this direction, it will make these connections. So by this simple mechanical connection also, you will be able to control the direction of the rotation of this motor, right? So primary thing that we are supposed to control for the motor is the direction and the speed. And you don't have any option to control the speed over here, because either you will be making the motor on or off. Motor speed will change if you change the voltage that is being given to the motor. So the current drawn by the motor is directly proportional to the torque that it is going to produce. And then only I will be able to change the speed of the motor. So this kind of arrangement will not give you the speed. Only you have to judge from the motion of the robot. You just release the switch and then you retard it, and then whenever you want to accelerate, then again power it and it will start moving. So that is the method that you can control the speed of the motor, and then control the direction of the motor rotation. So all sort of rotations can be done with this kind of a control. So you just have to operate it manually with the thumb, and then you will be able to control it. Let's talk about the relay, because somebody was mentioning about the relay also. What exactly is the relay? Let's have a quick look at this, because this is again a very important element in the electronics we use these days. So relay is just an electromechanical switch. You understand? A relay is an electromechanical switch. What we have seen, this is a mechanical switch because I'm just operating it manually. So you need an operator to do this operation. But when we talk about the relay is just an electromechanical switch. And the good feature of the relay is the isolation, the voltage isolation on the two sides. Let me just explain you. This is a very important element. Can I see the hands who know what is relay? Anybody familiar with this device? But I just pasted some pictures also over here. So anybody familiar with this hardware? No? Not so good indicator. At least you should come out with this understanding. I am sure that those who are making electronic circuits, they may be understanding this. Please raise your hand to indicate that you are aware of the relay. Yeah, so one, good, at least one person come out that, yeah, two, I can see that. Aditya, Asmin, yeah. Yes, Biani. Why you are so late in responding? Yeah, you are just waiting for first hand to come up. So I will request my staff and my colleagues to raise the hand first, and so that the other people will also be following it. So good that at least I see 6 hands coming up. It's nice that you understand the relay. So relay is a electromechanical device. Only point I would like to emphasize over here is there are two important elements of the relay. One is the coil and another is the contact. So if you understand this, you'll understand the relay. You can see this is a relay coil and these are the relay contacts. So if you just look at the physical design of the relay also, these are the two terminals and this is the coil part on the relay. And on the other side, you will see there are the terminals and there's a contact made with these terminals in this case. Good. So what is the purpose of the relay actually? Why we would like to have the relay? Again, I just want to understand from those who raise the hands. Can they just mention why we need a relay? What is the advantage? What purpose it is going to serve?
Using relay, we can control higher currents using signals.
Good, good. Yeah, so very good, very good. You have responded very nicely. So our understanding, as I was saying, I was emphasizing that you have two isolated circuits. You have a provision that you can control two isolated systems over here. So let's understand what are these two isolated things. One is when I say isolated means they are not galvanically connected. It means that they are not wired together. It's a very important aspect. So these contacts, what you see in the relay, they are completely independent of the coil. There is no physical contact. Physical means they are not electrical. There is no electrical contact between these terminals on this side and the coil terminal. So it means that I'm creating a galvanically isolated connections over here. And how it is operating now? So relay coil, which is here, which is a kind of an electromagnet. And on the other side, you will be having a contacts. So what will happen? So when you are not energizing the coil, you all understand the electromagnet, I am sure that. So whenever you are not giving any current to the coil, this common terminal, which you can see here, with the help of a spring. So there's always a mechanical spring here actually. So there's a spring over here, which will be keeping this common terminal connected with this one terminal. And that is what we call normally closed. NC is a terminology which is very common. So normally closed connection means if you're not powering the relay coil, your connection is made like this. So relay coil is connecting because there's no power, there's no electromagnet, there's no electromagnetic force. Only because of the spring force, it will be keeping this common connected to the NC. That is one connection. Second connection, if I power on the relay, if I give a current to this relay coil, it will get energized. It will get the coil converted into the magnet. It's an electromagnet will be there. And it will be pulling this armature here. It will be pulling this armature towards it. So if you can see here, this element get pulled towards the coil. And then as a part of this, this contact will change. Now your common will get connected to the anode. So what you have seen that the relay terminals are changing mechanically, basically, because of the electromagnetic force. And they are making these two contacts, either this contact or this contact. The relay coil is operated by a different electrical circuit. So that is the advantage. My relay coil is not electrically connected with the relay contacts. The advantage that I'm going to get over here is that I can operate any load, any voltage, any current on this side. So that's the biggest advantage for the robotic people actually. Now we are talking about the motors. So any voltage, any current, you can directly provide onto the contacts. I can talk about 12 volt here. I can talk about 15 ampere current over here. Now, what I will be doing, I will be utilizing these relay terminals. I will be utilizing this relay terminal part to just deliver this. Now, how I will be controlling the coil? I will be controlling the coil with my controller. So what I can do, I can control the coil with the controller, and I will be able to deliver the different voltage. I'm running a logic at the 5 volt, but I will be controlling a load at 12 volt. I can operate the relay coil at 5 volt. I can make the heater in my room on and off, which is taking 230 volt and maybe 10 ampere current. So that is the advantage of having a relay. It's a very common understanding that all of you should get, that there is no physical, no electrical contact between these two sides of the relay. It's an isolation. So this is the something, but again, the problem is not solved. Actually, even having a relay, your coil is not so so much easy to operate by the IO from the controller itself. Still, it requires some current, which is more than what your controller can source. So 10 milliampere, 20 milliampere. Normally, the coils requires a 250 to 500 milliampere. So again, we need to take care of this coil, how it is to be operated. So there we use the transistor to control this relay coil. This transistor is being used as a switch. So I'm sure that this is a very basic configuration of a transistor, that you can use this transistor as a switch to control the relay coil. And then the relay will be able to control the load. That is how this circuit simply depicts. It's a very simple understanding. Your load is connected over here. Your logic circuit is connected over here. The transistor is helping you into operating the relay coil. Transistor can help operating your motors also directly. Please understand this. What I'm talking right now is through the relay, but it's possible that you can directly operate the motor also with the transistor, that we'll see in a short time. Now, it says that don't forget these. Whenever you build these kind of circuits, there are certain minimal elements we need to take care. Can anybody tell what are these two elements and why they are being placed?
That is, one of that is flyback diode. It protects from the back EMF generated.
Yeah, great. So this diode has been kept because I'm operating an inductive load here. My relay coil is not a resistive load. It's an inductive load, and I'm sure that all of you have learned the back EMF. The moment the current withdrawn from the coil, there's a back EMF. Any kind of a polarity change on the transistor will damage it. So we need to safeguard that, and the diode has been placed to just protect that. So very good, Asmin. And why we have placed this 1 kilo ohm resistor here to the base of the transistor?
To limit the current.
To limit the current. Good. So now we are taking care of what my controller can deliver, and I will be adding few semiconductor devices over here to control the load which I am supposed to operate. So motors are being controlled over here. Transistors is basically used to drive the relay coil, and then I will be adding a 1 kilo ohm resistor to limit the current that it can take from the controller pin. So that is how these two elements are very important. If you miss them, if you miss this 1 kilo ohm resistor, you will burn out the controller pin. If you missed out this diode, you will burn out this transistor. So that's how the electronic circuits need to be designed very carefully. And these are the very common understanding everybody should have, whether you are from mechanical or whether you are from a computer science. Whenever you are working on the robots, you should have a basic understanding of all these elements. That is the point I just want to emphasize. Let's move forward. Now, using this kind of configuration, I have seen that we are just able to operate one contact over here. Now we will be combining these configurations to build the robot control again. So what I have done, I have designed it to control the robot. So on and off control can be done with the help of one relay here. So what you can do, you will be just controlling the power that is supposed to enter into the motor side. So one relay combination is being used to control the power. Another with a DP-DT relay. The single pole, single throw means there's one common, one NC, one NO. That is what the SPST relay is supposed to do. When I say DP-DT relay means there are two set of this. So this is one set over here. This is another set over here. So you can see there are two common, two NC, two NO terminals over here. They are all operating in one go with the relay coil. That is what you can see over here, right? So this way I will be able to control the direction with this input over here, because through DP/DT, earlier we have used switch. This time we are using a DP/DT relay. So DP/DT is just a designation for the contacts and the moving element inside the device. So here we are using a relay. So with single coil, I will be able to change over 2 contacts over here. So with one transistor operating the relay coil and this 2 changeover contacts, I will be able to control the direction of a single motor. And with one control, I will be making a motor on and off. So you get to some extent. Still, I don't have a flexibility to control the speed over here, because that is not coming anywhere. I'm only able to control the direction of the rotation of the motor, right? Now comes the era of a semiconductor devices. So we still want to get rid of this relay if it is not required. So purely solid state devices can be used to control the speed as well as the direction over here. So whatever the function that relay was doing, we can do it with the help of a power transistor. That is what I was mentioning. And the same can be done within a MOSFET also. So these are used in a configuration as a switch. Yeah, that's the important part. Yeah. Yeah, correct. So we are now coming to this understanding how you will be driving a load with the help of a power transistor or within a MOSFET. That is how it is making a purely sim, because your relay is still having a moving element. It's an electromechanical device. There is a certain life, there is a certain limitation, there is a certain switching speed. That is very important part. What is limiting there? If I would like to control the motor speed by on and off, I would not be able to do that, because the switching speed of the relay coil is limited. You can't have that 10 kilohertz or even 1 kilohertz kind of a switching available through that. And why we need switching? I think those who understand PWM, they understand it. We would like to reduce the voltage into the relay, into the motor coil with the help of the pulses actually. So because my controller is only able to generate the digital signals, so with the help of digital signals, I would like to reduce the voltage that can be delivered to the motor, and that is being done with the PWM. So those who understand, it's nice. Those who not, they please at least spend some time in understanding what is the PWM, how it can be, because we will not be able to cover everything here in the class. So that is the idea. So now what we are able to do, the same configuration, we are using a motor here, and you can directly give a motor voltage over here. So that is how, so if I'm supposed to operate this as plus 12 volt, I can directly give plus 12 volt. Again, the same functionality, if you try to visualize, is there. So motor voltage is coming to the motor. On the other side, I have to sync, basically. The current has to sync from here. That is how I am using an NPN transistor over here. So the path of the current will be like this. Based on the base input, the path of the current will be, and this current that will be passed through this circuit is dependent on the gain of the transistor and the current that is being drawn at the base. That is how the transistor is supposed to work. And in this case, if you provide the low signal, the transistor is not on, the motor will not be running. Whenever you give a voltage, then there's a current passing through this and the circuit will complete and motor will start rotating. So same protection again, because we would like to protect this inductive load, the transistor from this inductive load. So we place the diode over there. We want to limit the current to the base of the transistor. So that has been limited by the resistor over here. So now good thing is that now I will be able to perform the same functionality as relay was doing, but I can switch this input very fast. So instead of giving this one single on and off signal, what I can do, I can give a repetitive pulse signals to this. What I was just doing, I'm trying to make the voltage or the current available to the motor and making it off, making it so frequently on and off that the average that is appearing is depending on the duty cycle of the PWM. So how much time you are making it on and how much percentage you are making it off, that is basically deciding what is the average. So if I'm making 50% on, 50% off, I will be just averaging out the voltage. This is plus 12 volt if it is going. If I run within a 50% duty cycle pulses over here, my motor will be experiencing in a roughly 6 volt. And that will help you in controlling the speed. So that is the advantage, that once you have a transistor or solid state device like a MOSFET also, I will be able to switch the input very fast and I will be able to control the speed of the motor. Direction you have understood, speed you have understood, that is something you require actually. So that is the good part. Now let's come how it can be done for a motor for a bidirectional motion control. And at the same time, you will also be able to control the speed of this. So this is the configuration with the help of 4 devices. Now we are moving from purely from the mechanical control, the on-off switch control, the relay control, now moving to the completely solid state, because our intent is to control this speed and the direction with the help of a microcontroller or the microprocessor board. So this is again a purely solid state switching devices that we are supposed to use. Either you will be using a MOSFETs like this, or you will be using a transistors over here. So what we have done, we have used the 4 switches over here. So this can be done initially with the help of switch to understand, but then these are the 4 solid state switches that we are using, which are the MOSFETs over here. So what I will be having a control inputs to these 4. So I need a 4 control inputs here. Please understand, I need a 4 control inputs over here to make these 4 devices on and off. Now I have connected plus 12 volt over here. So let's, whatever is the motor voltage, I will place it here. And then this is the 0 volt. My motor is sitting here. Now you understand the philosophy of controlling the direction of the motor, that if you connect plus to plus, you will get a clockwise rotation. If you connect plus to minus, you will get an anti-clockwise rotation. So our intent is that this plus 12 volt should get connected to this. So what I have to do, I have to make this device on. So this plus 12 will be available to this motor. At the same time, the other side go to the ground. So that is how I will be just making this. So if you just made these 2 devices on, make the current flow like this to the motor, motor will be rotating clockwise. Now, just to change the direction of the rotation, I have to just make these devices off now. And I will be energizing these 2 devices. So what has happened in the solid state, what I have done, I have given this plus 12 volt to the motor on this side, and I have drained the current from this to this side. So there now the current flow direction is reversed to the motor. The direction of the rotation will also change, the anti-clockwise. So that way, by just controlling these 4 inputs, 1, 2, 3, 4, so Q1, Q2, Q3, Q4, you will be now able to rotate the motor in the clockwise and anti-clockwise direction. And if you add on an additional device over here, which will be generating the PWM, and then this motor voltage will not be a purely DC, you just give them the PWM signals, then I will be able to control the speed also. This is the basic philosophy of controlling the speed of the motor and the direction of the motor. Now these 4 inputs can be given to your controller board. Use any of the 4 digital inputs, and then you can use this to control the PWM, 1 PWM signal for the speed, and 4 signal here for controlling the this configuration, so that you can control the clockwise and anti-clockwise. Most important part, you need to understand this configuration is appearing like an H. That is how it is commonly known as H bridge. Good that. So using discrete devices, you can build this circuit all your own. But semiconductor industry is still helping you to get this everything built into the one single IC. And that is what we call the H bridge. So H bridge ICs are available for different current ratings. So you can see that you will be having only 2 pins given over here, PWM pin and the direction pin. So if you give a 0 direction, so logic is also embedded. Instead of having these 4 pins controlled by the controller, they just made it very simple that you will be getting 2 signals here. One is for the PWM, so that you can control the speed of the motor. One is given as for the direction control. So internally, there's a logic basically to make this 1 input and convert it so that it can make 2 transistor on, 2 transistor off. So that is all inbuilt into this. So that way, one single IC will be able to help you in controlling the speed of one motor. Now, once we understood the H bridge configuration, then they put 2 H bridge into one device. So one semiconductor device having dual H bridge. So many times we normally run the differential drive robots. So you will be supposed to control 2 motors only. So this single IC L293D will be able to give you 2 H bridge configuration inside it, and you can connect the 2 motors, and then 2 inputs basically used to control the 2 PWM signals and 2 inputs for the directions. So that way, one single device can help you in controlling the full robot the motion control is being taken care by this hardware. But this is having a current limitation. L293D can't be giving you large current over here because the transistors that are being used here are not the power transistor to give you large current. So in that case, it can only source the 600 milliampere. The another variant is available 754410, which can give you at least 1.1 ampere. So depending on the current, the small bots can be able used to be controlled for this from this kind of a devices. Fine. So that's how you will be having another IC L298. So these are some of the motor driver ICs available, and this is able to give you 3 ampere actually. So if the motors will be operating at 3 ampere, you can use this for that configuration. So these are the motor driver ICs available. For higher current actually, now the motor driver boards are also available. So this is the board that we are using in our robot. It's a smart Elex 15D smart motor driver. Now you understand the philosophy of the driver board. I'm sure that by looking at this board, you can easily figure it out what is being used over here. Fine. So now you can see that this is a regulator over here. These are the MOSFETs that are being used here. If you can see here, again, this is used to control 2 motors over here. So that's a good thing. So the same H bridge is being made like this using the 4 MOSFETs. One H bridge is being built over here. Another H. So whatever you would like to design, that is already onto this board. So these kind of ready boards are available, and selection of this MOSFET will decide how much current you can use. So in this case, 15 ampere continuous current you can give, and 30 ampere peaks can be taken out of this board. So if you get hold of this board, I think you are ready to drive your motors now. You can write the logic basically. So these are the different interfaces that you can understand from this board. Some of my colleagues will explain you in detail. And that is the way you just hook up the motors, you connect the battery, and then you connect with the controller, and you are ready to make your robot moving now. So that's a quick understanding. So all about the motion is simple this. If you have a controller, if you have a motor driver like this, you will be able to control the 4 motors. So I need 2 such boards actually. So in our design, we have used 2 such boards so that I will be able to control 4. If I'm using a differential drive robot, I will be just happy with 1 board and 1 controller, and I will be able to make it run. So that's all the basics that I would like to share with you in this. Thanks for this. I have taken a long time, just try to give you a basic foundation for today's understanding. Then my colleague, Dr. Venkat and Kalahar will be taking the sessions further to give you more insight how the robot has been built. Yeah, so let me take quick questions over here. So Gauri is raising the hand. Yes, Gauri, what is your question?
Sir, actually, we discussed about the different ways in which we can control the motor.
Correct.
So can we use SSR, that is solid state relay, in case of normal EMR, that is electromagnetic mechanical relay?
So normally solid state relays we use to switch the AC loads basically. See, whenever we found an application of the solid state relays, we prefer that we will be able to operate an AC load from a DC logic input. That is where the SSR fits much better in the application. Otherwise, if you are getting in a same DC-DC converter like this, or the SSR, which are just giving you an advantage of controlling a DC load, yeah, that's the same thing. Inside also the same circuit, what we have just shown you, that those semiconductors are there in the SSR.
Okay, sir. Thank you.
Thank you. Yeah, Dhananjay?
Sir, I want to ask for motor drivers. Can we use Adafruit motor shield with Raspberry Pi?
Yeah, so this motor shield certainly can be used. Yeah, from Raspberry Pi, you can use this Arduino shield. Only thing what you have to just understand, what is there onto this motor shield actually. So again, you will come across these kind of devices will be there. You will just understand which are the pin interfaces will help you in controlling the direction and the PWM pins. And then you need to just check what is the ratings of those MOSFETs or the transistors that are being used. Same Arduino shield can be easily used with the Raspberry Pi. There is no limitation as such.
Yeah, okay, so.
Okay. Good. Any other question quickly on the motor control part? Because that is the basic thing that we are supposed to implement, and that is what we have interfaced onto this itself in the current robot. Good. So if there's no more, I will request Dr. Venkat to take the session further. Good. Thank you. Thanks for the patient
one more
listening
question,
and
sir. I want
participating.
to
Yeah,
ask,
yeah,
sir.
please, please.
Sir, for in Robocon, what do you suggest? Like, do we use the Raspberry Pi or the Jetson Nano? What should we send motor
Yeah,
better?
so let me just give you some briefing on that also. So Raspberry Pi, you see, it's a processor only, right? So it has some capabilities. You can connect a Raspberry Pi camera to that. So at least you get some camera feed also. Raspberry Pi is also able to run the ROS. So that flexibility is also available. You can run a Ubuntu and you can do that. But still a large compute is not possible onto the Raspberry Pi. So for example, if I would like to deploy any of the machine learning code, actually, some kind of an AI part, till you are not doing any AI data intensive operations, Raspberry Pi is good enough to operate the robot. There is nothing to worry, because your image processing to some extent at certain speed can be done with the Raspberry Pi itself. With an 8 GB RAM, I think it will be able to do some processing for you. But if you want to do, for example, LiDAR, we are talking about the LiDAR, and later on we would like to put in a dual camera, and the vision processing will be more compute intensive. And you would like to do some kind of a learning algorithm also onto the board, then the Raspberry Pi will not be able to handle it, and you have to go for the Jetson Nano. Right?
Yeah, understood, sir.
Okay, thank you. Good. So, and if there are no more questions, over to you, Venkat, for the next session. Yeah. You are not audible. Please unmute. Yeah.
Yes, yes. It's very good lecture, sir. It's a good thing that you made my job easy for the next session.
Good, good. So let's have a good start of the day. That's how now they understand the electronics, and they at least able to correlate the discussions that we'll have during the day. So good.
Yes, sir. Yes, sir. So we would like to take a small break. We'll be back at 10:30. So, and we'll start how we'll discuss about the connections, electrical connections, and I'll be also sharing some what kind of battery to be chosen and this thing based on the requirements and such things. We'll discuss all the way.
Correct. So we'll spend half an hour in discussing that electronics part, what you will be explaining, the connections that we had made on the robot. And then after 11, I will just talk about the electronymatics.
Okay.
And I think Kalar can discuss about the code in the post-lunch sessions then.
Yeah, post-lunch. Post-lunch.
Okay, then we'll discuss more on the code side.
Okay.
Is that okay, Kalar?
Sure, sir.
Okay, thanks. I think thanks. So let's have a break and then join back at 10:30.
Yes. Share my screen. So welcome back. So today we'll be discussing about the electronic circuits and connection diagrams, especially for the robot. We have been discussing about the design and to develop a base platform. So in this, I hope everyone can see my slides.
Yes, Venkat, you are audible and visible.
Yes. So in this, we'll see how the power distribution is being done connection wise with modular level. We'll show how these connections to be done, and we'll see how the Arduino Mega board is powered up, and similarly how we are using Mega and ESP32 connections, and again the encoder connections and the driver connections, and we'll quickly take some questions and we'll discuss. So first, starting with we have a 12-volt battery we have taken. I'll come with the what do you say the rating of this battery. So here what we see is these the connections on the battery are in parallel, because the driver circuits here in green and the buck converter, so they are in parallel, and the motors on driver D1 and D1 like M1 and M2 are driven by this driver D1. They're powered internally from again this one. So this 12 volts is again applied to this motor driver. Similarly, this driver also where M3 and M4 are connected. And here we are using a buck converter to step down this 12 volts to the required voltage. So Arduino Mega can run work on voltages between 7 to 12 volts. And again, we are using the inbuilt regulation or the power distribution on Arduino Mega, where we have 5 volts as well as 3.3 volts outlets, voltage outlets, so output pins. So here we are using, as we have discussed in the previous session by Jasser. So he explained that he showed us that ESP needs 3.3 volts. So instead of making another buck converter or stepping down from 12 volts, we are directly using this one. And also it will be helpful one way because the communication we are establishing, especially in the serial communications or the encoder connections, there should be a common ground here. Why? Because these E1, E2, E3 are the encoders on the motors, individual respective motors. So these also need supply. So we have a 5 volts. Since the current drawn by these encoders is very less, we are using this 5 volts output voltage, which is available on this one. Now coming to how we have to choose a battery. So now we know like what is the power consumption or current drawn by this individual at lower level. Let us say these encoders or motors or the even you say in total Arduino Mega and ESP, we know how much power the current they draw. So basically, when you see you need to give at least 2 amperes to 3 amperes of source which is suitable. And as we have seen previously, these drivers, these motors need 10 amperes of current. So because these batteries connected in parallel, whatever current is drawn, they can be added and we can decide on how much time we want to run. The longer the duration and the battery capacity comes into picture. So here we can use a battery of like we can go to 18,000 mAh or 24,000 mAh. So the more capacity you are taking, the price also increases. And also there are several variants: lithium polymer, lithium LiFePO. So such kind are there. The stability is also important. And here we have used a buck converter directly. A 12 volt battery can run your Arduino Mega, but we can set this voltage at minimum because the consumption of the peripherals are using very low. They're drawing very low current. So you can either set this at 7 volts or 8 volts like that, so that we can save power for longer durations comparatively. So this is the overall connections, how the red line is the positive and black represents the ground. So how these connections are being given. So instead of going to physical terminal wise, we wanted to show this one so that it will be clear how from a single battery source, how we distribute the power. Okay, so going forward, we'll look into how we are stepping down. We are using a similar, as sir has discussed, we are stepping down these 12 volts to 7 volts at the minimum. And we are using one screw terminal connector jack connector, and we will be powering up Arduino Mega. So here from 12 volts to 7 volts. So though Arduino Mega supports 7 to 12, we want to, based on the peripherals, peripheral devices which are connected on this one, and how much, at what rate your program is also running, like the computational current also consumption also depends on the computational effort, the while loop or this how fast quickly it should run. So that also draws a lot of power current. So based on that one, we can set this one so that this will be stable. So we recommend to use a buck converter because this will be dropping down. Okay, this will be dropping down drastically when it is being utilized by the other devices. So a stable supply should go to your controller, either any of the controllers. If you talk about Raspberry Pi or if you talk about ESP, that should be perfect. So this is how in our robot, which we displayed yesterday, and physically we'll also be showing them. This is how the connections are. And then coming to the communication between ESP, here in this one, we are operating the robot using a PS4 wireless controller. So this PS4 needs a Bluetooth connection, and since the Arduino Mega does not have a Bluetooth or Wi-Fi compatibility, because we wanted to integrate, we can use a USB dongle, USB shield, and then put a Bluetooth dongle, and then we can do that. Instead of making the making a bigger one, we wanted to use a ESP32, which has inbuilt Bluetooth, and if required, we can use these also to communicate, because we are communicating through a serial, we are establishing a serial communication between Arduino and ESP. So the terminals here, if you can see, the first zero, it is denoted by 0. So the first serial communication ports, and here we have connected it to RX2 and TX2, and the power, as we discussed, we are using a 3.3 volts, which is available on the Arduino Mega, and we are connecting it here. So how we are programming ESP32 to communicate, Mr. Kalhar will be discussing in the next session. And coming to how the connections are given to the encoder, which is on the motor. Okay, so the encoder looks like this. This is a Hall effect based encoder. So we have 2 channels to be communicated, and we are using here the supply, as I told you, that the supply for the Hall effect encoder is also given from Mega, which consumes very less power. So that's why we are directly powering up the encoder through Mega only, and the motor, these pins are connected to the motor driver because this will run the motor. These connections are to the motor. So here, if you see, we have used digital pins here, 14 and 18. Okay, channel A and channel B. So this will enable to count the number of what is happening. So the number of rotations which are happening, and similarly we have for motor 2, which are connected to 15 and 19, and this is given to driver 2. And here 16 and 20, this is also given to driver 1 of motor 3. Sorry, this is driver 1, motor driver 1, motor is M2, and there is a typo here. So this is motor 3 on driver 2, and these channels are 16, 20. And similarly here motor 4 on driver 2. Okay, channels are 17 and 21. So we have used 14 to 21 connections here. So I listed down here. So here we can see motor M1, M2, M3, M4. So these are the channels and these are the pins which are connected. Okay, so these are where the data to mega from these encoders are coming up. And we'll also demonstrate how to test the encoder, whether there are offsets in the encoder, a kind of simple calibration we'll be doing on the encoder. Okay, so next we have the driver circuit connection. So if you see here, as Professor Jha has explained, here we have the PWM signal and the direction pins for each motor. So one represents motor 1 on the other side, motor 1 on the other side. I'll come to this section. So I would like to explain here. So we configure these pins. If you see the blue lines, we configure them as, for example, 7. These are PWM lines which we are configuring, and this DIR need not be, because this is just a direction. Digital logic is sufficient. So this is there. And the other side, if you see how the motors are connected, as we have seen in the first slide, from the battery, this is the main supply to the entire board. So we have 4 2 on both sides for these either side of this supply terminals. So M1B and M1A, where we connect the motor M1 and M2. So here, without the code on Arduino, we can test which direction the motors are running and this thing. So for example, here we have test buttons M1A, M1B, M12, M2B. So once you connect the motor physically, once you connect the motor M1 and M2 physically and battery here, you can simply push these buttons to see in which direction they are rotating. For example, M1A, it should be in forward direction. So M1B will be in reverse direction. So this way you can test whether your motors are communicating and your driver circuit is working or not. And there is a reset configuration to reset the entire board. So the driver board, there is a reset button. And here we have dip switches to configure which mode we are going to operate on this driver board. For example, you can control this or communicate with this one using an RC, a wide radio control joystick. You can control your motors, or you can directly program this with the Arduino. You can connect the RxTX and you can control it through Arduino also. Here what we did is we are using a pulse width modulation mode, where we are sending the signals from here, from Arduino to driver, and those are run on this, the motors connected here are running, will be running on this one based on the PWM generated in the Arduino. So we'll also show how to select this dip configuration physically. So though it is not here. So based on this selection of this either 0 or 1 on the direction pins, as Professor Sunilja has explained, the MOSFETs here will be selected, powered up, and the direction of the motor is controlled in particular fashion. So this circuit is for basically for motor M1 and M2 on driver 1 circuit. So similarly, and here we have used channels 9-8 and 7-6. So 9-8 are for motor 1 and 7-6 are for motor 2. I summarized this on the table also. I'll show them. So next we have for motor M3 and M4 on driver 2. Similarly, motors are connected here. Sorry. And here we are using channels 5, 4, 3, 2 to control the motor. So here if you see, we have for driver 1 circuit, on the driver 1, on the driver side, we are connecting the motor on MA1 and M1B terminals. And using the test buttons, we'll see the direction. We have to see whether they're rotating in forward direction and reverse direction based on the configuration we'll have. We'll show that part also. And on the Mega side, these motors are connected to 9th pin for controlling the PWM and 8th pin for direction control. And for M2, 7th pin for PWM generation and 6th for direction control. And similarly in driver 2, we have motor 3 and motor 4. Pin number 2 is connected to control the motor 3 speed, and 3 is for driver direction. And similarly 5 is for direction and 4 is for control. So as you see here, we have started with the power. So we have basically we have shown how the power lines are connected. So in the physical demonstration, we'll show you how the power lines are connected and how the motors are connected to the driver circuits, as well as we'll show you, yesterday we have shown you how to configure the encoders with the motors. So in the second half, Mr. Kalhar will be discussing about the programming side. And so here one more thing I wanted to discuss is if we want to go with additional sensors. So what are the other sensors we wanted to connect to the Mega? So or any other controller. So if you look at the Mega board, you can see several other pins are there, as Professor Jha has shown us that there are analog pins. So there are to monitor how your base platform is vibrating or what are the different shocks it is taking. You can connect an accelerometer. So accelerometer modules are available which generate 0 to 5 volts, and you can use an inbuilt 10-bit ADC on this analog signal is converted as a 10-bit output, and that you have to again convert into the digital value. Hexadecimal value has to be converted to numeric so that you can understand what is the acceleration on that one. Other than that, there are smart sensors like MEMS-based smart sensors which communicate on other protocols, communication protocols. One kind of protocol here we have is I2C based. So if you see this SDA and SCL line here, you can connect around more than 128 devices on these two lines. Okay, you have a separate the SCL is the clock line and SDA is the data line, and a common ground also should be given across that one. So you can connect several sensors here. So these several sensors on the same two channels. So what happens? They are addressable devices where you can simultaneously get the data from that. Okay. But when you see here, if you see like we are communicating in the case of ESP. Let me go to the ESP. You are doing a serial communication. It is a dual communication, but it is limited only to one device here. So you cannot connect parallelly another device onto this ESP. Suppose if you have such sensors, you can connect several of them and you can monitor, because we have 4 wheels and you want to see the condition of your 4 wheels. You can connect using an accelerometer is a good example. ADXL 345 analog devices, which is an I2C based breakout boards are also available, and several IMU sensors are also there, which are based on I2C. You can connect them to those lines because this board has that feature. And other than that, we have one more configuration. It is SPI, serial peripheral interface. So there also we can come in. What do you mean? We can connect only one device to that one. So when it comes to your other sensors, which can be incorporated in this Robocon challenge, is you can connect an line following device, which has all these line detecting sensors, like which have these photo diode and photo transmitter, receiver transmitter configuration, and other obstacle avoidance devices like ultrasonic or proximity. Those also can be connected. So there are good sensors which communicate on I2C based on. So if you can find out in the market, like you can for best communication or for best control, though this Arduino is only sequential programming is possible in Arduino, you can configure using I2C based communication, so that that is there. And one more thing I wanted to add here, the basic difference between what Professor Sunil Jha was discussing, like when we are starting with a bare metal, like your hard programming your code into Arduino every time using someone has told that you have an Arduino IDE. Okay, so your hard programming. When it comes to Raspberry Pi or Jetson, you have an inbuilt operating system, and even they have more than one core. So if you are very good, this is especially targeting, I'm speaking to your counterparts in specialized in IT and computer science. If you are using Raspberry Pi or Jetson Nano, parallel or multi-threading can be done, so that at the same time you can optimize the usage, the multi-cores, and you can at the same time you can collect data from or control devices at the same time. Here in Arduino case, it happens only sequentially. So there are several advantages using OS based like Raspberry Pi or Jetson Nano, and there are disadvantages also. For example, Raspberry Pi does not give a analog output, so you have to go with though here, even in the case of Arduino Mega, in our application, Robocon application, 10-bit ADC is sufficient, but you can go with I2C based A to D converters, which go up to 16-bit resolution. So there are 16-bit resolutions, I2C A to D converters which are available. Similarly, as I was telling, several configurations can be made, but many of them should be explored based on the application we require. So thank you very much. So if you have any questions, I'm ready to.
Yeah, Venkat, there is one in the chat if you can respond.
Yes, sir. Could you please give us some brief about what will be the connections with Raspberry Pi of these components? Yeah. So if you are using Raspberry Pi, let me go in slideshow mode. So if it is Raspberry Pi again, ESP32 is not required because Raspberry Pi has inbuilt a Bluetooth. Okay. And if it is coming here, PWM communicate you are giving these readings. So digital IOs are available, so you can directly connect them. And when it comes to the driving circuit, I have to check the number of pins which are there for PWM control. So otherwise, externally, I have to connect a device to control the PWM. Okay, and yeah, these are the differences which we have right now. And analog, as I covered, analog device, if you have to, there is no analog port on that one. If you have to read any analog sensor data, you have to use an A to D converter additionally. So they in market, there is a good, I'll type it in the chat box. So there is a good A to D converter, which is I2C based. Let me ADS ADS 1115. So breakout boards are there.
Sir, can I add something?
Yes, yes.
So this driver is a special one. It has inbuilt serial communication available. So we can control it using serial also.
Yeah, serial way also we can control, but the way of programming will also matter. If you are doing it in serial, there is a, we'll discuss that part in the second half. There is a way of sending a particular packet in a data in a specified dedicated packet, like with some address, start of packet and end of packet. You have to send that data into that. You have to rearrange whatever numbers are there. You have to rearrange them as a packet and send the data in serial communication, because you'll be communicating through Raspberry Pi. So as I said, because you want to, in this case, what is happening is motor M1 and M2, motor M1, whatever communication you are doing, you can control M1 and then M2. In Raspberry Pi, what happens is you can control simultaneously M1, M2 along with M3, M4 if you do multi-thread programming or parallel programming using the multi-cores which are available. So that is possible in Raspberry Pi, but you have to see how the, if you go for Raspberry Pi 8 GB RAM, that is possible through RxTX serial communication. So any other question? Is 4 GB will be enough to do path planning using LiDAR and image detection simultaneously? And which selection will be good? Raspberry Pi 8 GB or I say Jetson Nano 4 GB is better than Raspberry Pi 8 GB, as Sunil Jha sir has also mentioned that.
In such case, always go for the Jetson Nano if you have this kind of requirement.
Yes.
And any other question?
Any other question? Otherwise, we can move to the next.
Yeah, so what I will suggest, Venkat, because we capped half an hour break after 11 to 11:30, I would like to request that if you can shift it, the break towards it. So I will start now and try to finish by 12:30.
Yes, sir.
Then there could be a lunch break till 2. That will be better.
Yes, sir. Meanwhile, we'll arrange here the live Zoom because we want to demonstrate on the robot also.
Correct. So that part you can arrange. Till that, I will continue with the session.
Yes, sir. Thank you very much.
Thank you, Venkat. Thanks for covering it nicely. At least you'll get some idea about the connections that are being made on the robot. With the basic understanding which I was sharing and what Dr. Venkat has added, that how these connections are being added physically, then it comes to complete the basic electronics that on your robot. Not much difficult actually, as you understand the pin diagrams, pin connections that are available. I think that with that understanding, you can switch on any of the board actually. It doesn't make much difference whether you use the Arduino or will be using ESP32 or Jetson or maybe the Raspberry Pi. The physical interface can be made as you understand which pins it's supposed to be connected. I hope that will be clear to all. Good.
Yes, sir.
Nice. Thanks. So what I will do, I will just continue discussion further, and what I would like to relieve you a little early for this lunch break. So the next session I was planning to give you a quick idea on the electropneumatics actually, because I saw there's a lot of development happened in the use of electropneumatics in the Robocon robots. So again, before I start, anybody have some idea about the pneumatics, electropneumatic circuits? No one? Have you used any of the pneumatic cylinders earlier? Good, at least I can see one hand. Good. So fine. I think so. What my intent today is to give you a brief understanding. Those who are not familiar with the electropneumatics, we look forward that you should at least get some basic understanding, because these days to apply an impulse force, large force, throwing an object, the driving in a mechanism, you may not be able to do with the conventional motor basically, because there's a certain advantage of using a fluid power technology, and the pneumatics is one of the fluid power technology. With the help of a circuit diagram that you can create, you can easily apply large force, and by releasing the actuators with the compressed air. I think that's what you have seen. So what I will take you through this another 1 hour, give you some insight into these components, how they can be put together. Maybe you will be able to build these circuits very easily. The way you have understood the electronic circuits, I think the same way you should understand the electropneumatics as well, because these are going to be an integral part of the Robocon robots. Right? Please raise your hand and then let me know wherever you have any questions so that I can stop and explain you. Right? So before we talk about the electropneumatics, this is something we need to understand. It's all the fluid power technology. You have already seen the electrically powered systems. The way you have seen the electrical systems are given the 12 volt, 5 volt, and then with the help of a large current and the voltage, you will be delivering some power to the motors, and then motors will be converting that into the mechanical torque, and then you will be utilizing that torque to drive the robot. Now, when it comes to the fluid power technology, then we will be talking about the fluid power in the form of the two fluids which are commonly used, hydraulics and pneumatic. That's a liquid and gas. But none of our robots are supposed to use hydraulics, so let's not worry about that right now. But the devices like this, actually, you may see that these excavators and even the complex gripping arrangements, they are using hydraulic systems to some extent to apply large force. Wherever there is a need of a large force, I'm sure that you all have understood that hydraulics is the one that is going to multiply the force, and then it will be able to lift a very large weight as well as apply the large deformable forces. So when we talk about the fluid power technology, we are certainly dealing with these three things actually. How you generate the fluid power means conversion of the electrical or the engine power into the fluid power. Then finally, you would like to transmit it to the actuator, and then finally take an action. In between is the control part. So these three things we are supposed to understand quickly. Whenever we talk about the pneumatics and hydraulics problem, these kind of systems are common in the industry. So you are supposed to control these actuators. So this is a gravity fed magazine. If you understand the functionality, you have a stack of the boxes over here, and we used two actuators. This is one actuator, this is another actuator. So that with the help of actuator, we will be able to push these blocks actually. That's the idea. So if I have to attempt this kind of a problem, I should be able to create a circuit diagram through which I can control them. Right? So these actuators are being driven by the compressed air or the pressurized fluid. That is how we call them hydraulics and pneumatics. So let's have a quick look at that. In terms of the basic actuator, it's very simple. The design, if you look at it, it's a cylindrical barrel with a piston inside it. And then this rod is moving in and out. So this is a piston rod that is coming in and out of this actuator. On the two sides of the piston, you will have a flexibility to make the fluid enter into this. So if you make the pressurized fluid entering into this side, it will be pushing the piston back, and your rod will be moving downward. So your weight will be moving downward. Then if you want to lift the weight, what you have to do, you have to just make the fluid enter from this side and come out from this side. If you just reverse the change of the direction of the flow of the fluid, this piston will be moving upward and the rod will be lifting the weight upward. So that's a basic actuator understanding. That's not a complex system. It's a simple cylindrical barrel with a piston, rod, and two openings. That is very important. These two openings are very important. The way you have seen that we were reversing the direction of the rotation of the motor with the help of the direction of the flow of the current. Same thing you can apply here with the flow of the pressurized fluid. You will be able to control the direction of the movement of the actuator, either forward or backward. That's an advantage that you will have here. Okay. The complete pneumatic systems, because we need to quickly understand the various elements over here. That is how the whole pneumatic system is supposed to operate. So actuator is one part of this. So this is your actuator, which is one part of the whole system. So even whatever robots you have seen in the Robocon, they are all building this thing, except what they are not doing. They are not basically having this system in place on the robot. What they are doing this, they are generating the compressed air, and they are utilizing the reservoirs. So on the robot, you have seen that there are a lot of reservoirs placed in the form of the bottles, plastic bottles. So they are storing the compressed air into these reservoirs, and they will be utilizing this compressed air depending on the functionality they want to perform. So if you see here, robots will be carrying this part, the reservoir, the valves that you require to control the pressurized fluid, and your actuator. So these are the three things that they are on the robot. These are the other things that are on the ground station. So they always have a compressor. They will be compressing the air and filling into these bottles to the desired pressure. And then certainly you need to control the pressure also, how much you will be maintaining into it. So that's how they will be performing these tasks on the ground. So these are these things which are being carried on to the robot. If you see the all components, how they will be operating, certainly you need a reservoir. First of all, you need a reservoir. Then you require controls, and then you will be making this fluid available to the actuators through the piping and tubings. And finally, they will be operating. So the critical element that you need to understand is the control valve actually. The rest of the things are very straightforward because you have an actuator, you understood that. Compressor, you already know that, and the reservoir, depending on whether it's in a hydraulic system, you will be having a reservoir and then pump. In case of a pneumatic systems, you will be having a compressor and then reservoir, because we will be storing the compressed air. Right. When we make circuit diagrams, as you draw the electrical circuit diagrams, these electropneumatic circuit diagrams will be drawn like this. So these are the elements which are being shown over here. This is a pneumatic control only. There's no electronics over, no electrical systems over here. So earlier days, people used to build the logic also pneumatically. So there are different type of elements. Quickly give you a glance on this so that you will understand the basics over here. So this is a power component which will be converting the fluid power into the mechanical power. So you will be having a linear actuator like this. Then control element is the valve, like your H bridge. So there are also a direction control valves available, which will be controlling the flow direction of the fluid. So this valve is basically converting the input signal into the appropriate direction of the flow of the fluid. And then rest of the combination over here, these are the combination of the different elements to build the logic. So these are the processing elements over here. And then you may be having some inputs captured from the operator also. So you can have these push button valves. And then certainly the supply elements is the filtering the air and then regulating the pressure over here. So mainly, if you understood, actuator is a critical element and the valve is the second critical element. That's all. Rest is the compressed air, that how you are dealing with. Quick look at these actuators, as I have already explained. So it's a simple cylindrical barrel, and inside the barrel is a piston. So if you see the cut section of this, this is your barrel region. And inside that, this is a piston with a sealing, actually. That's how it has been done. And there is a piston rod coming out, which is connected to the piston here. And there are openings, as I was mentioning. So these are the rod end opening. These are the cap end opening. So this is the front part of the actuator. This is the rear part of the actuator. So through these two openings, I will be able to make the flow entering into the cylinder. Now these cylinders are of two types. One is the single acting cylinders and another is the double acting cylinders. What is the difference over here? In the single acting, you will have only one port actually. You will be only having a one passage to make the fluid enter into this. The other side port is free actually. There's no source that is being connected here. Only it is a vent which will be allowing the air to come out. That's all. And it will suck the air inside it. But there is no pressurized flow entering into this side. So this is a single acting, but there's an internal spring that you can see over here. So with the help of a spring force, piston will be maintained at the rear end. And whenever you make the pressurized fluid enter from this side, it will push the spring and then the rod will be extending. The moment you stop the flow over here, it will go back. That's how the single acting, because you are having a provision to control the flow in one direction only. Double acting is that you have a provision of two ports over here. There are two ports, so you will be able to control the forward as well as the backward motion of this piston. So both direction you will be having a control on the motion of this actuator. So that is what the double acting cylinder is. So single acting, double acting, depending on the functionalities. Here we need not to worry about how the rear, retraction motion will happen. Only you have to extend. And the rear, the retraction will happen because of the spring force, right? Because these are something little different than what you have learned. So if you have any issues in understanding, please let me know. I can quickly repeat the basic understanding also. Because what I want, you need not to go for an additional learning to at least use the electropneumatic system in your robots. That can be easily understood by what I am just trying to explain. There are rotary actuators also, again, not used in the robots that you are using, but there's a possibility that you can use the pneumatic motors also. So there's the same way you have an electric motors. For large torque, we are using hydraulic motors in a very heavy systems like an overhead cranes and other. But in the electro-pneumatic systems, we rarely use a pneumatic actuator because electrical system is giving you better control. So, but there are rotary actuators normally for the pneumatic drills, and other people are using these pneumatic motors as well. Philosophy is same, that you will make the pressurized fluid entering into this motor, and then it will be rotating clockwise or anti-clockwise. Each device, we need to understand the symbols, because when we create the circuit diagram, we have to take care of the symbol part. The three type of valves commonly used, because this is the important part, where whenever you are building a pneumatic circuit or electro-pneumatic circuit, you have to deal with the valves. In the electrical systems, electronic systems, you are dealing with the gates. So here we are dealing with the valves. So that's how you should understand it. Three main functionality. What we are controlling here, we are controlling the direction. That's the most important part, that I am controlling the direction. Because I would like to extend the actuator, then I would like to retract the actuator as whenever the functionality is required. So maybe it is then coupled with the mechanical linkages so that you will be either lifting something or it will be pushing something. So that's how the actuators are an important part. Right? So you will be controlling the direction of the motion of the actuators with the help of direction control valve. Then there are other type of valves. To control the speed, we will be using flow rate control valves. So flow valves are there. This is the flow rate control valve. To control the pressure in the system, we will be using the pressure control valve. There's a pressure regulator. So these are the three type of valves: direction valves, pressure control valves, and the flow control valves. So in all pneumatic systems, all electro-pneumatic systems, you will come across only these three type of components. In the controls, you will be having these three components. So direction control, flow control, pressure control. Pressure is basically controlling the force that it will be applying, because the pressure decides directly the force coming out of the actuator. Flow control is deciding the speed of the actuation. So you will be adjusting the, normally if you are not putting a flow control, the speed is very high. So wherever you would like to have an high speed applications, let's not place the flow control. But whenever you would like to control the speed in a low speed, gradual movement, then you will be going for the flow control. You can just put a flow control, restrict the flow, and then you will be able to see the lower speed coming up. Rest is the direction control. So you will be seeing the different type of direction control valve that I will explain. The common is the check valve. It's a simple unidirectional flow, so that you can make the flow possible in one direction only. It's like a diode in the electrical circuit. So you may know that diodes in the electrical circuit make the current flowing in one direction only. Other direction, there is no flow of the current. Same is with this valve. With the configuration that you can see here, like a ball or the poppets like this, you have this configuration. Because of the spring force, you will close this opening, so no flow. Then if you make the large pressurized fluid coming from here, it will apply against the spring force, then the flow is passing through this. But then the other side, it will be not be allowing, because you will be pressing the ball against the seat. So this is a ball. If you make the flow enter from this side, it will be pressing this seat again. And then it will not make the opening available for the flow. That's how it's a unidirectional only. It's mostly we are using for the reverse flow protection actually. So sometimes the circuit will not allow the reverse flow. So that is how it is being used. So it's a free flow like this. If you can understand from the symbol itself, this is a symbol that is a seat, and then you will be having in a ball. So if you make the flow coming from this side, ball will be lifting and it will be allowing the flow. But from the flow, if it is coming from this side, it will be pressing the ball against this seat. So there is no flow. So there is a free flow direction. There is a no flow direction. So we need to understand from the symbol itself, what are these? They can be put in this kind of configuration. So it's very easy to understand. Now, let's try to understand what you get from what I was just mentioning about the check valve. Which configuration out of this? So let me say that this is 1, this is 2, and this is 3. In which configuration flow A to B is possible? If I would like to make the flow reach from A to B, out of these 3 configurations, which will permit that? You can put that in the chat also. Your response can be seen in the chat. I can just have a look at that. What I was explaining, based on that understanding, what you understand that in which direction flow from A to B is possible? In which of the configurations out of these 3? 1, more than 1, also possible. So if you can quickly respond. Please respond either on the chat or you can speak it up also. Good. Some of you are saying it is 1. 1. Good. Anybody saying 2 or 3? Okay. So everybody agrees that it is 1 only. If you can look at this, certainly what I was explaining, that when the flow will come from A, this side it is blocked actually. You cannot allow the flow because the ball is now pressing against the seat. So there is no flow. So only possibility is that flow will be coming like this and reaching to B. If I look at the A, again it's immediately restricting. There is no flow coming from this side to this side. So it's already blocked over here. But in case of this configuration, it will allow the flow, but then the second is blocking. So that's how neither of these two will be allow the flow from A to B. Only the first configuration will allow the flow from A to B. Right? So that's good. You understand the basic functionality of this check valve. The second type of valve, the first one is this, what we call a poppet type valve. Poppet means this moving element is known as poppet here. This is the poppet, and then you have a spring on top of that. So either it's a ball type or it's a poppet type. So it means that you will be applying a pressure, it will be lifting, and then it will be closing it. Good. Now what we want to see, the other type of valves are the spool type valve. These are the spool type. So there is a moving element, as you can see here. There's a moving element with a varying diameter. So there's a large diameter here. There's a large diameter here. There's a small diameter here. So like this, there's a rod with a multiple diameters inside it. And then you will be able to shift this rod. Actually, you will be able to move this rod inside the wall. And at the same time, you'll also be having some opening onto the wall. Like these are the openings on the wall. It means that what it can be used, you will be making the pressurized fluid coming over here. And then depending on the position of this spool, what I was just making, either it is fully left or it is fully right. Depending on the position of this spool, you will be allowing this pressurized line to go either to B or it will be going to A. It means that if I will shift the position of this spool, I will be able to connect this line, pressurized line, which is coming from P either to A or B. These options are there. So this type of valves are the spool valves, and these are the most commonly used valve in the direction control. Right? Some of them are operated like this. So you can see it's a 2-port only. You have only 2 openings, this, and then they are internally connected like this. We'll see how this symbol is to be drawn. So this is again a same type. So you have 4-way valve. It's a 4-way connections possible, that A to T flow is possible and P to B is possible. And same is with this also, that pressurized line can connect it to A, or then B get connected to the T is the tank basically, or the reservoir. Right? Let's understand this symbol first. Now I will be placing this valve like this in the cylinder circuit. So this is my actuator. Now you have understood that I would like to either extend it or I would like to retract it. Right? This cylinder has these 2 openings. So I have just connected these 2 openings to the wall. So these are the lines that you have to connect. And what else I have to do? I have to connect this line to the compressor, which will be making the pressurized fluid entering. And then this will be the tank, that is the reservoir. Right? Now, when we have these valves, what is our intent actually? We need to always understand why we are doing this. So let me understand what we want. So we are saying there are 3 positions over here. This is 1 position. This is a 2nd position. There is a 3rd position. Means I can hold the spool inside the valve in 3 positions. Either of these 3 will work. Right? So our intent is that what we want, we will be able to control the motion of the cylinder either forward or backward, or just halt it, stop it somewhere. Because many times we want to hold the load also somewhere. So if you don't allow any fluid entering into it, the cylinder will be in that particular position only. Right? So in this case, what we will do now, if I have to extend the cylinder forward, let's say that I have to just extend the cylinder forward. And so this is your P, this is your tank. Right? So what I'm supposed to do, what connection I have to make? Can you tell? So how can I make this cylinder moving forward?
Sir, P will be connected to A.
Okay.
And P will be connected to T, that is the drain.
Great, great. What will happen if I will not connect B to T? If I just only make the P connected to A, will the cylinder move?
So the other side air needs to get exhausted while we are filling.
Good. So you understood this. So I think everybody will be now getting this point. See, unless we drain the fluid from the other side of the piston, whether it's in a compressed air will allow some extent because till the air get compressed, but then beyond that, it will not allow. In case of a liquid, actually, it doesn't allow anything. So then it means it's not allowing any kind of movement possible on the actuator. So that's very important that whenever we would like to make the pressurized fluid entering from this side, it will also be draining from the other side. That is what we want, right? So in this case, now we want this configuration in one of the position of the spool. So what we will do, we will be just making this connection in either of these three positions. So what we can assume that, let this be one position where I would like to extend the cylinder. This could be the another position I would like to retract the cylinder. And third position is something where we would like to hold the cylinder, that don't want to move the cylinder at all. Right? So these are the three positions required. Now let's try to make what connections just we discussed. So in the first position, we need to draw the arrows to indicate the direction of the flow. So we have understood that P will be allowing flow to A and my B is taken to the T. So if I draw these two arrows, the symbol is complete on the left hand side. If whenever you look these arrows, now you can understand what is happening here. So the line which is coming from the pump, we will not be writing the names on the actuated position. So A and B, P and T are written on the center position only, because these are the unactuated positions. 1 and 2 are the actuated position of this valve. Actuated means whenever you will energize, you will make the flow possible. So in this case, what will happen in this case, whenever you shift the spool to position 1, this is how the connections are being made. It means that now P is connected to A and B is connected to T. So the cylinder will be able to move forward, right? So this will give me the forward motion of the cylinder. If I want to retract, now who will tell me what should I connect? Can anybody tell what should I connect now if I want to retract the cylinder?
So P to B and T to A.
P to B and T to A or A to T. This is very important actually.
A to
How
T,
you
A to
draw
T,
the
A to
arrow,
T,
that
sir.
is important. Yeah, repeat it.
A to T, sir.
Yeah, A to T. That's nice. So what we have to do now, P to B, this is the arrow I have drawn. We understand that A, B and P and T, their positions where they are. So P to B, we have drawn this arrow. And the other is from A to T. Don't say T to A, otherwise the arrow direction will change and the symbol will be wrong, right? So this is the right hand side, and this we will be using for the retraction. So we understood that. Now when we shift the spool to the position 1, it will be forward motion. If we shift the spool to 2, it will be retracting the cylinder. Good, understood. So now only thing left out, how we will be shifting the spool. That's the only thing. And we also understand what will happen in the center, what we want in the center. If I have to block this cylinder movement, if I have to hold this piston anywhere in between, what I'm supposed to do? Where the line P and T should go? And how the connection of A and B should be there, so that I will not be making any motion in the middle position. Who will tell this? Dhananjay?
So connect both to P.
Both to P, then what will, yeah. So you would like to maintain the same pressure on both the sides.
Yes,
right?
sir.
That's a one way, but see, believe me, the motion will happen in that case.
Sir,
See,
can
when you say you will connect A and B to the P, will there be a motion or no motion?
Sir, there will be motion.
Correct, because the area on the piston is different on both the sides. Please note that, because motion is possible with the help of force. Even I am applying the same force here, pressure here, I will be applying same pressure over here. What will be the situation? The cylinder will start moving forward. Because the area that is on this side is much higher than the area that is available on this side. So for the same pressure, because area is different, force, this is higher than the force on this side. So it will, resultant will be pushing the cylinder forward. Dhananjay, you got this?
Yes, sir. Now I got it, sir.
So it means that this will not help. Yeah, Aditya, you were telling something. No?
Sir, what if we include a check valve in middle of that?
No, check valve basically I will not recommend, because you can't control it actually. Because if you place a check valve into the line, then it will always be allowing one directional flow. The limitation here is that I need a flow on both the direction. Like this also will be required. This also will be required when the cylinder is moving forward or backward. So I can't place the check valve right now here. It's a very simple configuration inside the valve itself. You have to just block the ports, nothing else. What you can do, you can just block this. So whatever is the fluid on the both sides of the cylinder get locked inside the cylinder only. And once that, it will not be allowing the flow either coming from this side or not coming from this side. It will be locked actually. That's how the locked cylinder configuration. Then there is no motion. Rest is left out. What you will do with the pressurized fluid, you can just divert it to the tank. That is one possibility, but we don't allow the oil. Oil is fine, but we don't allow the air to leakage in this way. Otherwise, what you will do if you connect the compressor to the environment, it will be just throwing all the compressed air to the air. So what we can do, we can even block this also. You can just block this and this. So if I have all the ports blocked internally at the center configuration, my pressurized fluid will not be coming into the wall. It's not going out of the wall. Basically, it's coming, but it's not going out of the wall. At the same time, I will also be blocking both the side of the cylinder so that there's no motion of the cylinder. So this is basically the center locked position. There's no motion. So if you shift the spool to the position 1, you will make the cylinder moving forward. If you shift the spool to the position 2, you will retract the cylinder. And whenever you release this and it will be in the center position, there is no motion. This is something basically what we require in the actuator control. Hope this is clear to all. Good. So these are the way we normally mark these positions. And this is very important to understand how many positions are there in the wall. So there are either 2 positions or the 3 positions. So walls are normally designated by this 2 position wall or 3 position wall. So 2 position means you will be only having 2 positions. One is the default position and another is the actuated. This is the default position. This is an actuated position. In the 3 position, what I have drawn, you will be having 1 default position and there are 2 actuated positions because you will be shifting either to 2 or either to 3. So this will be making forward, this will be making backward, and this is the locked position. So these are the 2 types of walls that you will come across. And these numbers, these nomenclature is known actually. So whenever you go for purchase of these walls, you should tell what type of wall you want. It's a 2 position or 3 position. And then how many ports you require on the wall, right? So that is how the naming of this wall will also be there. So I am sure that you might have heard about the 5x2 wall, 5x3 wall, 4x2 wall, 3x2 walls. These are the naming convention for these walls. So whenever I say 5x2, it means these are the ports actually on the wall. Ports means there are openings on the wall. How many openings are there? Then second number is indicating how many positions of the spool. So now onward, whenever someone will tell you that they have a 4x2 wall or a 3x2 wall, you can easily figure it out. What does it mean? When I say 3x2 means there are 3 openings on the wall and there are 2 positions of that wall. So 3x2 wall will be there, right? That's how you can now understand the basic nomenclature of the direction control wall. Good. Then how they will be operating, there are multiple ways of actuation. So these walls internally, if you can see, they have the same configurations like this, what we were discussing. So these are the positions that are being marked over here. And this is how it has been implemented physically. This is a cut section. So as I was saying, this is a spool with a multiple diameters inside it, the variable diameters, higher or lower diameter. And then there are passages around this is being created as a part of the design of the wall, so that you will be able to get these kind of flow possible, right? So if you see, there are multiple ways the wall can be actuated: manual, mechanical, pneumatic, hydraulic, electrical. So just have a quick understanding of that. Manually, normally when people operate this lever, whenever people operate this lever, they will be able to control the valve and the cylinder. So normally whenever you see these excavators, they have these manual valves. They are shifting the levers, they are operating the bucket of the excavator. That's how this valve will be controlling the direction of the motion of the actuators. Then mechanically, something is moving and then you will be having another profile which will be deciding that, which will be actuating the spool, and then the valve direction will be changing. So these are the mechanical actuation. So some kind of another element that is being used to move the spool inside and outside of the valve. So these are mechanically actuated. Then there are the pilot actuated, means whenever we are using the same compressed fluid to actuate the valve also, we call it a pilot actuated. But normally, whenever we are creating a purely pneumatic circuits, we are using pilot actuated. Otherwise, most of the pneumatic, the electro-pneumatic circuits, we will be actuating with the solenoid. So the last one, yeah, I think I missed that. Sorry. So the another one is the solenoid. Yeah, it is there. So you can have the solenoids also, which is not appearing here. We'll show it when we go to the electro-pneumatics. But same spool can be shifted to either of these two directions with the two solenoids that can be used. So electrically, you will be pulling this spool, and you will be controlling the direction of motion of the solenoid or this spool inside it, and the direction of the flow of the valve can be controlled. That is what is the electrically actuation will be there. So in pneumatics, electro-pneumatics, we will be having those electrically actuated spools inside the valve. So that also we'll see that when we discuss the electro-pneumatics. There are few more types of the valves which are being used, may or may not be used in the robots, but you can at least have a quick understanding that you can create an OR and AND configurations with this type of valves. This is a shuttle valve because there's a ball inside this which is shuttling between the two ports. So if you see here, this is the position. If the ball, the pressure will come from this side, the ball will be shifted to this side and the flow will go like this. If the pressure will come from this side, then the ball will be shifted to this side, it will allow. So either of these two will be allowing the flow to go from both the sides. Fine. So that's how the OR gate configuration is there. So inlet 1 or inlet 2 make the outlet pressure available. And that is how the OR can be implemented. This is an AND configuration also, which is done with the dual pressure valves. So internally, if you see, this valve can be used like if the pressure is coming from here and from here, then only this flow will be going like this to the outlet. Actually, if you see here, these are the passage, then the outlet will be getting a flow. If there is only one directional flow, if the inlet 1 is applying, so this member will be resting against this. So then there is no flow going out to the outlet. Same is with the other side, that whenever the flow will be coming from this side, this will be stopping the flow against here. So no flow will be going to the outlet. So either inlet or outlet, inlet 1 or inlet 2, if one of them are coming, then outlet will not be getting a pressure. This is a simple AND gate configuration. So pneumatically also it can be done. These are the pressure relief valve or regulators you always prefer to use on your robots. It's a safety measure. Whenever you are filling the reservoirs in the robot with the compressed air, you have to limit the pressure in there. So that is the important part. So these kind of safety valves can be used. This knob will be used to adjust the pressure. You can see from the dial how much pressure is there. Normally, when we use this, we will be using 3 to 4 bar. That will serve most of the purpose unless you are trying to apply the large force. So this 3 to 4 bar, you can limit by this knob, and then you can easily see this here. So this is a safety device. If you will not apply this, then the pressure will build up in these bottles, and then some of them may blast actually. So that is how safety is important. Your reservoir should not have pressure more than certain value, depending on the strength of the bottle that you are using. So this is another important element as a safety should be added onto the robot. Now we'll understand what all elements to be put together in the circuit diagram. So there are some elements which are the signal input elements. There are some elements which are processing the signal. Then you have finally the actuator will be there, and then you will be controlling the flow direction with the signal output device. So these are the various elements that are being used. So I will be directly coming to the electro-pneumatics that is more relevant over here. How the signal flow will happen in this case, right? So in this case, you will see there are possibility that you will be getting a signals coming from multiple input elements, maybe the push buttons or maybe the relays. And finally, you will be using this direction control valve here, which is a signal output element, so that if you energize this solenoid or this solenoid, you will be controlling the spool direction, and that will be operating this final power section. Okay. If I would just like to show here, if you have to build this circuit diagram, how you will do that, the logically how that will work. So you will be having an electrical signal control section built through the different relays, or maybe with the help of a controller over here. And with that, you will be now sensing the position of the actuator. So that if you see here, this is the actuator that you can see here, which is having a pneumatic connections like this. So pneumatic connections are there. So these are the two pneumatic connections from the valve. This is one pneumatic connection to this part of the cylinder. This is another pneumatic connection to the rear part of this. So you have used the valve here. So pneumatically you made the connections, and electrically also you will be making connections. So your solenoids, these are the two solenoids on the valve, which are connected to this control system that you will be using, either a relay, or it will be a microcontroller that through which you will be controlling this solenoids. So that way, two electrical connections to the solenoids, two pneumatic connections to the cylinder. We also would like to sense the position of the cylinder inside it, position of the piston inside it. So we will be using these two sensors over here. You can see these are two sensors over here. Through that, you will be sensing if the cylinder is at the extended position or at the retracted position. They are acting as an input to your controller. So your controller will be understanding the positions, and accordingly it will be actuating the solenoid, which will be shifting the spool inside it, and the pneumatic pressure will go into this, and then it will be driving the actuator. So this is the quick understanding of an electro-pneumatic system, how it has to be built, right? Just quickly give you an idea, these kind of electrical systems, though you may be familiar with, so push button switches that can be used. So these are the terminology I was using in the morning. Normally open contact means if you are not pressing, it is the open electrical connection. If you are not pressing, if it is already electrically connected, we call it a normally closed connection. And some of the devices will be having a changeover connections here like this. And then this is how the symbol is being used to represent them. Then various sensors we use to detect the position of the cylinder. That is what you need to do, detect the end position of the cylinder. Because, for example, if you find that the ball is being placed, so you will be using some sensor to detect the ball, then only you will be throwing the ball, right? So you can just trigger that also. The moment you get the ball is being placed, your controller will come to know the presence of the object. Then after that, it will be deciding the movement of the actuator. So that is the way these sensors will be helpful in sensing that, right? So there are various type of those sensors. Either the mechanically limit switches will be there. So many times for the collision of the robot, you can use these mechanical devices to sense that. So that's how limit switches can be. So they inside will be having a mechanical contact only, and whiches will be making the electrical current flowing in from the common to either NC or NO, depending on the ways it will be operating. So you will find that there are different means of actuation over here. Either a lever has been used, or the plunger will be used, or the roller will be used. So there are different configurations outside, but internally they will be just actuating a switch like this. Then there are proximity switches. Without any mechanical force, you will be able to sense some of the things. So they are available in the different configurations like a reed switch, inductive, capacitive, optical. So different sensors are available for sensing the presence of an object. So they can also be used in the robot for sensing some of the obstacles or maybe the objects in the robot. This is a reed switch which is operated with the magnet. So if a permanent magnet is brought closer to this contact, it will be just closing the contact. So with the mechanical means, without contact, you will be able to operate this contact. So normally we use this on the cylinder. This is the cylinder body. If you see here, there is a piston inside it. And we are placing this magnetic ring onto this cylinder, the piston. And this is made of aluminum. Please note that this is made of aluminum. So when the piston come in close vicinity of this, so if you see here, once the piston, because the magnet is there, it will close the contact. So you will be able to sense the where the cylinder is and where what is the position of this cylinder. So it's a very low cost option to detect the position of the cylinder with the help of reed switch. Electronic switches are proximity sensors are little costly because they are using an electronic circuit inside it. But then the connections that you always get is supply voltage that you need to provide, and then the output signal that you will be getting, whether the object is in close proximity or not. So they will be either the inductive proximity to detect the metal targets, There could be a capacitive proximity to detect the wooden target or any plastic targets. They can be able to sense the all kind of materials here, right? So these are the capacitive proximity. Then there are optical proximity, where you will be using this kind of sensors for just with the help of light beam, you will be able to detect the presence of the object in front of it. So these are some of the sensors normally used in automation, may be useful in the robots for sensing the vicinity without having a lot of image processing or others. Normally we place these kind of sensors to detect any kind of the obstacle around it, right? Pressure switch is fine. I think let me know. This relay I have already covered in the morning itself. So you'll understood what the relay is. That's how it has been explained again in the detail here. And we can place the relays in like this. Multiple modules can be used to place the relays, and you can make those connections through these relay modules. Now, important element we need to understand is this direction control wall, which I was explaining. This is an interface between the signal control that is coming from the controller, which will be your Arduino board or the Raspberry Pi board, through again the driver that you will be using a driver that I have mentioned in the morning. That's a power transistor should be used to drive this, or maybe the Darlington pair of the transistor will be used. So because it requires a large current here. Large current means certainly not that large, but maybe about 500 milliampere will be required over here. Again, you will be driving this solenoid with the help of an additional powered circuit, or maybe using the MOSFET or the transistor, right? But what you have here, you have two electrical connections over here, which you will be controlling through your logic in the electrical circuit. And then you will be having a pneumatic connections, which will be driving the actuator part. So that is how the two circuits are there. So these are the way the circuits can be built. That is what I just want to give you an idea. That whenever you have the cylinders connected to the wall, and then once you are energizing the solenoids, it will be just extending and retracting the wall. So only difference that is that the spool is pulled inside the wall, the solenoid, and it will be changing the configuration of the wall internally, right? So good, I will be just keeping some of the slides in the interest. So this is how the circuit need to be built. That is what I just want to demonstrate to you quickly. That how you will understand my circuit will be behaving and how I will put that circuit together. So whenever it comes to control the cylinder, for example, this is a single acting cylinder. So I have to select a wall. I will be connecting this tubing with the wall. And then this solenoid is being controlled electrically. So I will be using an electrical circuit over here. So for example, if I want to control it with the push button. So if I press this push button S1, 24 volt will be flowing inside the solenoid. And this 24 volt will be actuating the solenoid, which will be changing the valve configuration to this. And so this pneumatically connected line will now delivering the flow to the cylinder, and this will be extending. Overall, what you have understood that from electrical signal, I will be controlling the pneumatic action of the cylinder. That is how the electropneumatic circuit is supposed to work, right? So we slowly, so you can write the logic into your controller board when you want to extend, when you want to retract, and then you have to pneumatically wire them to operate them. That is how the whole circuit will be working. So slowly you will go for the double acting cylinder, single acting cylinder, and as your logic will be requiring more actuators, then you will be adding more pneumatic elements and then controlling the solenoids with the help of a electrical logic in the controller board, right? Just want to skip some of the things. I think that's all fine. Now, some of the circuits I just want to explain how they can be done. Yeah. So one is that you have pressed one push button, the cylinder will extend, press another button, the cylinder will retract. In the walls also, I just want to show one important aspect over here. These are the two position wall. If you see here, these are the two position. You will have one position, there's another position. It means that once you energize this solenoid, the spool will be shifted to this position. There is no spring actually. That is what I just want to mention here. There's no spring here. It means that once the spool shifted to this position, it will remain there whether you make the current available here or not. So once you shift the spool, it will be there. Similarly, whenever you want to shift the spool, you energize this solenoid and the spool will shift to this, and then without keeping the continuously current flowing into this, the spool will be maintained at this position. It means that I have to give signal only once. I need not to retain the voltage into that solenoid to keep the valve into that position. So that is what is known as double solenoid valves. These are the double solenoid valves. In case of a 3 position, you will always come across a spring because the center position is maintained by the spring on both the side of the spool. So at the moment you release the current from this, it will go to the center position. Same, once you release the current from this, it will again go to the default position is center, maintained by the spring. So that is how whenever you will be extending, you have to continuously flow the current into this. So that is what is you need to take care whenever you write the logic for those type of valves, right? So we can build these kind of circuits. So basic, I will show you some demonstration also from the lab. Automatic return stroke means if I press something, if I make the input available, the cylinder will extend, then I will be sensing the extended position and make the cylinder go back. So every input signal will make this one stroke like this. So whenever you will be ejecting, whenever you will be pushing something once, this is the way you can place this actuator in this configuration, and you can write the program to control the solenoids. And you will be sensing this extended position and you can use it. Oscillating motion is also possible. You can have a continuously oscillating cylinder in this direction. Right? So this is how you will be building circuit. My intent is that I will give you some idea on how to simulate. Before we actually build the circuit, what we normally do, we will simulate the circuit diagram. And there are software available, which I will recommend. You can also simulate your circuits, and then only you will be implementing them physically. Otherwise, you will do a lot of iterations making them physically. That's the only reason. To avoid that, you will first check the functionality of the circuit in the simulation. And then only once you are sure that this is going to perform this way, you can go with the physical implementation. So what I will do, I will connect with another system to show you simulation first. And then I will show you some of the physical execution of these videos also. Right? So just hold on, let me connect with another system. Yeah, so Mohit want to know how to control the stroke length of the piston. See, normally in case of these kind of actuators which I have shown, they are going full length. But what you can do, you can place the sensor on the actuator where you want to keep it. So if you don't want the full length to be traveled, what you can do, you can place a sensor, because right now we are placing the sensor at the 2 extreme positions. If you can adjust these sensor positions somewhere onto the barrel of the cylinder, then the control action can be taken accordingly. So the moment it reaches to that position, you can reverse the valve. So that way you can control the stroke length in these cylinders, right? So these are the proximity sensors. As I was showing you, these are the proximity sensors. So if cylinder is having a magnetic ring, so whenever you will be ordering the cylinder, you can just order that it will be having it. So most of the pneumatic cylinders may have the pneumatic permanent magnet on the piston. Then you can place these reed sensors only, reed switches. These are the low cost sensor that can be used. So reed switch can be placed onto the cylinder body, which I was explaining in one of the diagram, so that through that you will be able to sense that. Otherwise, what you can do, you can place the external switch, external limit switch. What I was showing as a limit switch, they can be placed outside. So the moment it will mechanically hit that, it will be retracting the cylinders. I will show you those demos in the lab. Right. So any type of sensor, either it will be mechanically actuated with the rod, or it will be the non-contact type proximity switches that can be used. So they can be placed onto the cylinder. Right. Yeah, Aditya, you have question?
Yes, sir. Sir, do we need to put the compressor tank on the bot, or do we just need to put the reservoir?
Yeah, so what you have to do now, you have to do a quick assessment of the how much pressurized fluid you require actually. The number of operations we need to see. See, one option is that the reservoir should be large. You will be storing the compressed air for all the operations you require for 3 minutes of the robot performance. So depending on how many times you are actuating the cylinder, see, every time you will be using the pneumatic system, it's an open loop. Actually, the air is not coming back. That's how you are just draining the air, right?
Yes.
So in that case, what you have to do, you have to keep count of that, how many times you are operating, what is the possibility of the leakage also. And then if you have enough reservoir, you don't need that actually. So compressor is normally don't need. That's how people add multiple bottles to store more compressed air for the operations. So that is always advisable if you can match your requirements with the compressed air reservoir only. But worst case, if you will be using too much, then you have to go with the compressor. Then it will be draining out your battery because you have to keep the compressor running. So even the 12-volt compressors are available, but then you will be continuously operating. The vibration of the compressor will be an issue. And then you will also be supplying continuous power to this compressor to run. So these are the challenges if you are running with the compressor.
Okay. Thank you.
Gauri, you have a question? Yeah.
Yes, sir. So actually, can we use Hall sensors as a limit switch? We were thinking of that.
Hall sensor will also be used because they are also sensing the magnet target or the metal target. So you can place them also. Yeah.
But sir, the problem which I thought was the wiring is very complicated. Like if we have it on extreme positions, we'll have a lot of wiring that needs to be taken care of. So is there any way we can simplify it?
Wiring anyway will be required. See, whether you place Hall sensor or whether you will place proximity switches, anyway, you have to connect them electrically. The another option is that you will be placing these sensing devices in terms of the valve in front of the actuator. Then there is a pneumatic connections required. What I'm just saying, wiring is anyway will be required to connect because they will be going as an input to your controller.
Yes, sir, but it is making a lot of mess. So I thought, is there a way to simplify it? That is why I'm asking.
So otherwise it will be just, see, in that case, if you are not sensing, then it's a timing based control actually. The other option is that once you make the valve on for some time, you will just automatically change the valve current so that it will be go back to the neutral. So then you will be just controlling with the open loop kind of thing. I will just energize the solenoid, make the cylinder move forward, and then automatically change the solenoid to take it back. So there's a timing based, there's an event based. So that's a way you can decide the program part.
Actually, the wiring for Hall sensor is a long one. So it is like being entangling a lot. So is there a way to organize it?
Yeah, Hall sensor, I will not still recommending. I will still be suggesting the proximity switches will be more simpler because those are not the complex systems. It's a simple reed switch can be used, or either of the inductive proximity switches can be used, or otherwise the limit switches can also be used if it is not creating a problem. See, normally when we go for the pneumatic cylinders, the clamps are available to place onto the cylinder in a nice fashion actually, so that you will be directly mounting the sensor onto the cylinder body. If you'll go by that, then the wiring will not be that cluttering. If you are preparing everything on your own, then there may be a possibility that you will end up in getting more wires around it.
Okay, sir, thanks.
There are ready sensors available which will directly clamp onto the cylinder. If you can try to use that, I think that will be better.
Yes.
Okay, good. Any other question related to the electropneumatics? Otherwise, what I will do, I will quickly give you a simulation experience, and then we will also demonstrate physically how it will be working. Right? So let me just do that. So I will be using a software which is known as Fluid Sim from the Festo, which I will be now sharing from the another system. Demo version is free. You can run it for 30 minutes and then you can create and simulate your circuits. That is how it can be done. So I will be just opening the demo version of this software. Some issue sharing. Let me share the full screen. I'm sure you are able to see this software environment. Though it is large screen resolution, so just. So this is the software which is in a Festo fluid sim. Is it visible? So shall I change the resolution of the screen?
So please increase.
No, it's not visible.
The font size at least.
No, see, unless I change that, because this is in a different system I'm operating, I will only change the resolution over here. We go to that, yeah. Reduce the resolution so that it will be little bigger to see. Yeah, let me see that. Is it better now?
Yes, sir. Yes, sir.
Yeah, so what I will do now, I will be just explaining you. This is a software which is Festo Fluid Sim that you can see here, Festo Fluid Sim. And what I will be having here, you can see the library of the components over here. So that you have a pneumatics over here, you will get an actuators over here. So that way, what I can do, I can just go and create a new. Right? So what I have to do, as I was explaining, I have to pick an actuator first. So I can go to the actuators library. I can pick up this double acting actuator, for example. I just pick a double acting actuator and placed it over here. Right? Now what I have to do, I have to just control this with the valve. So that's what I was explaining. We will go to the valve in this case, the pneumatics, just close the actuators. You will get a directional valves over here. You select a configurable valve. And as you understood, we are talking about the 4x2 valve or 5x2 valve. So we just take the 4x2 valve like this. So we have picked up this valve. Let me just see if you fit like this. So now you have seen that I have placed a cylinder. I have placed a valve over here. Now I have to make a connection. So what I will do, I will connect this to this line of the actuator. That is another side. I will be connecting to this another side of the valve. So these A and B connections I have already made now. On 1 and 3, what you require, 1 and 3, you have to connect the compressor actually. The compressed air should be connected here. So what I will do, I will go to the supply elements. And there's a compressor which I will bring in the circuit diagram here. And I've connected a compressor over here. Other end, I have to just keep it for the reservoir. So you double click it. You'll get an option what you want to do. So this is a symbol for the reservoir. I'll just do it, connect it with the reservoir. So these are the 4 connections as the valve understanding what we are having. We have done this. Now what I have to do, I have to define the actuation. Actuation is not being mentioned on this symbol right now. So what I will do, I will click on this valve. I will get the properties window over here. And from there, I can configure the valve. And what I was just mentioning, we will be adding a solenoid on the left-hand side. And we will be adding another solenoid on the right-hand side. Right? That is how it has been done like this. Right? So once you have this, just close this. Sorry, it has not been applied. So let me apply it also. So once I configure this one, electrical connection on this side and just okay it. So what I have done, I have two solenoids that I have placed on the two sides of this wall. So two positions can be controlled by this. Now, as I was explaining, we understood that when I actuate the left-hand side position, the cylinder will be extending, and when I'm operating this default position, it will be retracting. Right? This is the pneumatic circuit. Whenever we create the electro-pneumatic circuit, we'll first make a pneumatic circuits, and then we will be making an electro-pneumatic circuit. Right? So now electrical circuit I have to draw for this. Now let's go with the electrical. This is the pneumatic circuit I have already built now. Let's go with the electrical circuit part. So what I have to do, I will go to the electrical elements over here. So what we can do, electrical control, and I would like to have a power supply. So 24 volt line I can create. I can create a 0 volt line here. Fine. Then how, let me just show this functionality. So I'm not controlling these solenoids with the controller. If you will be controlling with the solenoid, so then you don't need this electrical circuit. What I'm just trying to show you with the help of a simulation, I just want to show you how it can be manually operated, but the same functionality you can do with the controller directly. You can use any of your Raspberry Pi or the Arduino, you can directly control that. Right? So that is how you can do that. So let me just. So what I will do, I will just pull some of the switch over here. So let me just go to the switches, manually operated. I can just bring out one push button over here. So I can add a push button. I will add one more push button so that I can extend with one push button. I can retract with another push button. Right? And what I can do, I can electrically connect them like this. You can make the electrical connection to this like this. Right? So this is done. So I have just placed two push buttons over here. But from these push buttons, what I am supposed to operate? I am supposed to operate the solenoid actually. So I need to bring out the solenoids also. So there's a solenoid available. Let's go with the. So this is the solenoid wall. I can just pick it up over here. I will be placing it here. This is one solenoid wall. I have added another solenoid wall. So this, then I will connect this electrically like this and make this electrical connection like this. So now what I have done, if you just look at this in totality, let me just fit to the window like this. So I have created a pneumatic circuit over here. I have created an electrical circuit over here. Now these solenoids which I have created in the pneumatic circuit are not being named actually. So they are not mapping. So this solenoid and this solenoid, we don't know. What you have to do, double click here, just give some name to this solenoid. So I will just give name 1Y1 to this solenoid. Make it okay. So this solenoid has been identified as 1Y1 and this solenoid in the circuit has been identified by another name that is 1Y2. Like this. So the two solenoids, I have just put the names. Now these names should appear here because this solenoid, what you are using in pneumatics, you have to just click it, which electrical connector. So I'll say 1Y1. And then again, double click on this one and it will ask which electrical connector. I said 1Y2. So like this. This is done. So what I have done, I have created a pneumatic circuit and then I just want to control with the two push buttons. So I have created a pneumatic circuit, electrical circuit for the same. Now I can check this in simulation. So what you can do, you can play it. So start this. The moment you click start at the top, you will see the pressurized fluid is being shown in the solid blue line. Electrical connections are being shown in a solid red line, right? Now let's see that if I press this push button, see that if I press this push button, what will happen? Like this. The moment current is flowing through 1 by 1 solenoid, the cylinder is extended now. Now, if you see the valve gets shifted, and even if I stop this flow of the current, the cylinder is still in the extended position. If I want to retract, I will just press this one, the cylinder will retract. So I can manually simulate this. Yeah, this is the way your cylinder is now being controlled. From one push button, it is moving forward. Another push button, it is retracting. So that is how I can easily simulate. So I just demonstrated the basic circuit simulation. Certainly, there are a lot of elements over here which you can place them and build a complex circuits also. And this is how we normally do the circuit simulation whenever we teach the automations or the basics of the automation. We normally teach these kind of circuits, but basics I have already given you the idea in this short span of the time. Right? I hope this is clear. So I will just stop sharing over here. Any question about this? Yeah. Is this understood? At least whatever short demonstration I just want to give you, is this clear to all of you?
Yes, it's clear, sir. Basic, it's clear.
Thank you. So what I will do now, I will just show you these in action. If there's any question, just let me know. If you are using air reservoir to store compressed air, then how to ensure that every stroke produce the same force? See, if you are keeping check of the pressure, that's a very important part. I was just showing you the pressure regulator, but there are pressure sensors available. So what my recommendation is that always try to add a pressure sensor in your circuit. So what you can do, normally when we perform the game or whenever we will be operating the system, we never keep account of how much pressure drops. See, the moment pressure start falling, your force will be reducing. So that's an important part. So what you can do, you can place a pressure sensor which is available on the line, and you can take that input into your controller. So what you can do, you connect it to the analog line, and then you will continuously reading that analog value, how much is the pressure in your system right now. Accordingly, you will come to know that how much pressure reduction is happening. So that's the way you can find it out. So once you are maintaining the same pressure, the force will be the same in the each stroke. It will not be changing. Only when the pressure drops, the force will be affected. Fine. Is this clear? Okay. Any other question you have for the electropneumatics? Otherwise, I will just give you a quick demonstration of the electropneumatic circuits. So let me take you to the system that we have in the lab for the simulation. Yeah, there are a few more. No, it's fine. Thank you. So let me just give you this idea. So this is the board where we normally test the electropneumatic circuit. So maybe some of your institutes may be having this. Otherwise, you can test it on a different platform also. Let's see that how this experiment is being performed. So you can just hear it explained by my PhD student. So you can just have a look at this.
So this is our double acting cylinder, which is the actuator. It has two ports. One is towards the rod end, the other is towards the piston end. So we have pneumatic tubes which have been connected to this solenoid controlled DCV. It is a 5x2 DCV because it has 5 ports. This is port number 1, which is the pressure port. Port number 2 and port number 4 are the actuator ports, while the tank or the reservoir ports are port number 3 and 5, right? So it also has 2 solenoids. This is the solenoid number 1, and this is the solenoid number 1 2 rather, I would say, and this is the solenoid number 1 4, right? So when solenoid number 1 2 is activated, the pressure from port number 1 is connected to the pressure port, and the port number 4 is connected to the exhaust port. Similarly, the same happens with when activating solenoid number 1 4. So now let's see how they have been connected. The piston end of the cylinder has been connected to port number 4, and this has been connected to the port number 2. The pressure is coming at port number 1 from a manifold which is present over here. We have 6 points to get a supply of air, and the pressure here is approximately 3.5 bars. So first of all, I switch on the pressure. The pressure is switched on, and I connect. So our pneumatic circuit is complete over here. Now let's make the electrical part of this circuit. So these are supplies of 24 volts and 0 volt over here. So first of all, let me give 0 volt to both the solenoids, because for working of a solenoid I will need 24 volt supply. So this is given in common to both of them. Now we connect power to the solenoids, which is controlled by a button. Right. So the power has been applied, but yet there is no movement in the cylinder. So if I press this button, if you see this solenoid 1,4 is activated. Since 1,4 is activated, the cylinder extends ahead. As we see over here, the cylinder is in the extended position since the button is pressed. Right. If I press another button to retract it, the cylinder again retracts back. So if I press the button number 1, the cylinder moves ahead. If I press the other button, the cylinder comes back. So this is a very simple problem that we have solved. If I press button number 1, the cylinder extends. If I press button number 2, the cylinder retracts.
So you have seen that this is the same circuit which I was simulating on the fluid sim. So this has been implemented physically on this board. So you have seen and understood these components as well. So that is same wiring, electrical wiring, and the pneumatic connections are shown with the blue tubings here, and the electrical connections are being done with the red and blue wires. I think that makes some sense. You will understand how physically it operates. So let's try to extend the implementation for another experiment now.
So now we are making the circuit, the electropneumatic circuit, for the next problem. So now the problem statement is that we want the cylinder to extend and reverse back immediately at the press of a button. Let us suppose that an operator is standing on a conveyor and he sees that a defective part is passing on the conveyor. When he presses a button, the cylinder extends, removes the part off, and the cylinder comes back to its original position just by the press of a button. So here we make use of a capacitive sensor which detects the position of the head of this cylinder, and it gives a signal to the solenoid. Right. So we have made only a small addition to this circuit, which is the capacitive sensor. So let's put on the pressure and start the circuit. So this is the button that I am using. Now if I press this button once, the cylinder extends and retracts back. So the moment the cylinder reaches the extended position, the sensor gives a signal back to the sensor is giving a signal back to the solenoid for retraction. Right. So now this is a very simple problem. By press of a button, the cylinder extends and retracts by press of a single button. Right.
So you have seen this demonstration, and this is very useful demonstration. Many times you want to push something and throw it. So this way, if you can incorporate in your robot, this cylinder can be used to throw a ball and then retract. So every time you give a logical signal to this solenoid, it will just actuate and then it will retract the cylinder back. Now, you were asking about the sensor. So this is the one sensor that you can place in front of it actually, but it's not always be required to place in front, because whenever you have object in front of the cylinder, then this sensor will not help. So in that case, we normally place these sensors on the body of the cylinder like this. So if you can see here on this cylinder, you can place the sensors on this cylinder body. That will be more useful, so that nothing will be obstructing the movement of the cylinder. So there are few sensors available which can be directly clamped onto the cylinder body. They can be used for this application, right? Similarly, you can modify the for the circuit to create a reciprocating motions. I just want to show that also.
Problem where we are making use of two sensors, one for detecting the retracted position of the cylinder, another for detecting the extended position of the cylinder. So what is the problem? That this cylinder should work consecutively in extended and retracted position. So I want 1A plus, that is extended, and then 1A minus immediately. So the moment the cylinder reaches at this point, it should give a signal to retract the cylinder. It should be an automatic cycle. No manual intervention is required. It should be an automatic cycle of extension and retraction, right? So what I have done, I have made use of two sensors over here. Both of them are detecting the position of the cylinder, and correspondingly that logic is being imparted to the solenoid valve over here, right? So let's start the pressure. Now I have controlled this circuit by means of a switch. So the moment I switch on the power to this circuit, you can see that the cylinder is moving ahead and retracting back without any manual intervention. So the sensors are giving signals to the solenoid, and they are alternatively giving power to the cylinder to extend as well as retract, right? So here we end our.
Yeah, so these are the few circuit implementation that I would like to show you. So you'll get some idea about what we are talking about, the pneumatics and electropneumatics, how they physically work, how we will be able to simulate these circuits. So this is something additional learning is required when you are going for the use of electropneumatic systems in your robots. So with this, I almost end my session right now. And if there's any more questions, I will be happy to address that. And I will encourage at least you think about some of these application in your robot, because they are very much required. Mechanically, with the help of motors alone, you may not be able to generate these kind of forces which are required in this case. So pneumatics will always be coming as an advantage for these applications. I hope this session will be helping you in creating your robots for the Robocon. And I just try to give you a quick glance on the electropneumatic technologies, how they are working, the different elements, understanding of the wall. That's all for this session. Yeah. Any question, I will be happy to respond. Yeah.
Hello.
Yes. Yes. Pankaj is saying something.
Yeah, he was on the phone, sir. So it was a good lecture. So electropneumatics, it is almost 15 years for me. I revised it in this occasion. So thank you very much, sir, for this good lecture. Hope this will be useful for the participants to incorporate in their mechanism for the Lagori. So should we continue with the next session, or
no? Now we will break it up. So now we'll take a break right now. Yes. And then again, I think start at 2 o'clock for the next session by color, and then explain the circuit diagrams. We can first explain circuits physically on the robot, and then we'll take them to the code actually.
Yes, sir. Yes, sir. We already set up the camera and everything here. So for
it's fine.
Demonstration.
Correct. Because we have absorbed that break, so we'll